My name is David Silver. Welcome to the IAA Knowledge Sharing event. We hope you find this to be a stimulating event. There's a lot of activities going on. First, Jim Bellingham will speak and talk about the overall IAA direction and progress. There'll be a short opportunity to have questions and answers with him at the end of his talk. Then we'll be going into the research activities, and you'll find them quite stimulating. There'll be 10-minute presentations, one after the other, but at the end of all of the research activities, there'll be a breakout session where you can actually go and interact virtual live with each of the PIs or all of them. And I think, if anybody has any opportunities or any desire to get more information to work with the PIs, it would be quite welcome. Afterwards, we'll be going to a discussion on ethics and governance, and Deborah Matthews will be presenting that. There'll be a set of lightning talks after that, a discussion about the flagship projects, a final wrap up, and then we'll go into another breakout session where you can actually talk about flagship projects. There'll be a town hall by Jim Bellingham, smart cities with Amber Mills, or ethics and governance with Deborah Matthews. And I say, or you can actually go in and out of each one of those sessions. I think you'll find it to be a stimulating event, and we hope you enjoy. Over to you, Jim.
Thank you, David. Okay. There we go. I hope my screen is up. So welcome to the Institute for Assured Autonomy knowledge sharing event. Our aspirations today really revolve around fostering connections. To put the bottom line up front, we want you to look at IAA as your advocates, supporters, and partners in creating a vibrant autonomy assurance community at Johns Hopkins.
Hey, Jim.
Yeah.
Sorry, I don't mean to interrupt. Your screen sharing is only showing the left side. Oh, never mind. Just fixed itself.
Did it just pick it up? Okay.
Yes, thank you.
Well, good. I'm glad we fixed that. So my name's Jim Bellingham. I'm the executive director for the Institute of Assured Autonomy. I've met many of you, but for those I have not, my background revolves around the development of marine robotic systems. I've developed, operated half dozen or so autonomous underwater vehicles. I've spent considerable time at sea operating them, co-founded Bluefin Robotics, and more recently participated and led senior advisory panels for the Department of the Navy. I'm attracted to intellectually hard, high-impact problems and great teams, and I joined IAA because it has it all. So let's get started on this. I don't think I have to tell this audience that autonomy is impacting every aspect of society, from our homes to our roads to our workplaces to our classrooms. It promises to revolutionize how wars are fought and how nations compete. It connects what we do in our laboratories to what happens in our communities in ways that are profound, yet difficult to anticipate. AI has the potential for both good and ill. The choices we make in our research will help shape the world that our children live in. As a consequence, understanding the impacts of autonomy and making sure it works, making sure it's secure, developing an ethical framework has to move to the center of the AI research enterprise. And these are the elements of we are calling assurance. So let's talk about assurance. This slide highlights two aspects. Number one, it's very expensive and lengthy to bring a complex product through the assurance process. And number two, if you get it wrong, bad things happen. As the complexity of the environment and the code increases, the number of edge cases that need to be discovered multiply, and statistical attempts to compute the cost of validation show that, for example, in the case of autonomous cars, you have to run hundreds of millions of miles, in some cases actually billions of miles, to statistically prove your autonomous system can function at the same level as or better than a human being. And that's not talking about the development process, that's talking about the assurance process. So in short, the traditional approaches to debugging complex software systems do not scale to autonomous systems, particularly where the software and data become inextricably linked in ways that become black boxes. So we need new technological approaches for creating, testing, debugging, incrementally improving, and understanding the internals of our autonomous creations. But assurance is a many-sided topic, and while the technical aspects are particularly familiar to this group, assurance touches on societal dimensions as well. So we all know technology changes society. It creates new industries and it transforms old ones. In the tech world, CEOs aspire to be disruptive, transforming rather than incrementally changing. But there are ample examples of disruptive technologies having unintended consequences. News aggregation on the internet, for example, has badly damaged the old news model with its editorial quality control, attention to reputation, and it's largely replaced it with a model where clicks rather than accuracy drive the economics. AI is going to amplify these changes, and part of our mission must be to understand our impacts and choose to work on the issues that will benefit and improve society. One of the aspects that I really have enjoyed about Johns Hopkins in my first months here is the diversity of our community, which has changed how I think about this assurance challenge. One of the several changes revolves around discussions with colleagues in the School of Public Health, in particular with Jeff Michaels, whose slide here I stole. I learned a couple of really interesting things. First, my public health colleagues look at autonomy as a solution for many of society's ills. So while I focused in my previous comments about some of the risks, we do have to keep in mind the brass ring, which is that these capabilities ultimately can make the world a much better place. Second of all, I realized that public health is more than an application domain. It's not just about removing, providing access to transport, removing food deserts, providing access to healthcare. It's also a dimension in the assurance space. So public health is impacted as you apply autonomy to mobility, energy, finance, healthcare, and more. So consequently, we very much view IAA as a school-wide or a campus-wide enterprise. And so we see our mission is bringing the broad talents of Johns Hopkins to the assurance problem. The central focus in the early years is really bridging between the applied physics lab and the academic campuses. And we have some major efforts underway to address policy and administrative issues to make collaborations across the campuses easy, fun, and exciting. I think there's always going to be challenges in working between these two different organizations, but I think we can make it a lot easier and function a lot more smoothly, and in effect break down barriers for movement of ideas, people, and formation of collaborations. But we also have within the academic campuses a range of collaborations with the schools, institutes, and centers that make up Johns Hopkins. And to give just one example, we're working towards a joint event focused on AI ethics with the Berman Institute, and you'll probably hear about that more from Deborah later. So our strategic vision encompasses embedding our research activities in a cycle, which include creating the tools and methodologies usable in what my industry colleagues call the real world, identifying unifying themes and opportunities for impact, and using those to catalyze flagship projects. And David Silberberg will be talking about those, engaging the larger community in discussion, and using the lessons and insights derived to drive new research ideas and innovation. The enterprise is large, the need is immediate, and so we see these external partnerships and translation as key inputs and outputs of the research cycle. IAA has had 2 great years. Carol LaPointe and Tony DeBura, directors for the APL and Whiting School legs of IAA, have developed really significant momentum. This slide outlines the breadth of engagement and the growing output of the enterprise. If you're part of this, thank you and congratulations on your accomplishments, which are particularly impressive as they've occurred largely during this time of pandemic. If you want to be part of this, then this event is for you. Reach out to those of us in the IAA leadership and in the office, and to the researchers whose talks you will hear shortly. So as we look to the future, I'm particularly excited about the opportunities to engage with industry, both large and small. This is a slide from my previous life where I ran a Marine Robotics Entrepreneurial Forum at the Woods Hole Oceanographic Institution, where I ran the Center for Marine Robotics. What you see here is on the left is a scatter plot of robotics companies in the greater Boston area. And the concentration of marine robotics companies is down there in that yellow triangle. I really believe that the research institutions of the future, which rise to the top, are going to be institutions which closely ally themselves to this entrepreneurial, innovative community. From a sponsor perspective, where else do you go than where you see sort of the combination of people who are working on the cutting edge of technology connected to the folks who are translating that out there to the marketplace and to the places where society needs it. So as a consequence, one of our focuses for the coming years is going to be to build our relationships with industry, both large and small. I think that there's two ways to think about the impacts to industry. One really revolves, if you're in the tech industry, about the issues that we've been talking about. As you develop autonomous systems, will they work? Will anyone buy it? Will it be allowed on the road, in the airways? And those really revolve around this issue of social license. And social license is, will society accept you're flying your autonomous taxi cab over a schoolyard or over your house? Those are essential things. So these billions of dollars we see being invested on the right really are assuming in many cases that the social license will appear and that the regulatory policy and ethical framework will emerge. Now, on the other hand, you may be in the target industries, and so you may be in an industry where you're not a tech company, but AI may impact you. And I show on the right there a picture of a parking garage, definitely not a tech industry, and yet something that might be impacted tremendously by changes in mobility and how we get around. So one of the things that those CEOs have to be worrying about is their business model under threat? So these are two existential risks, if you will, for the business communities, to different parts of the business communities, and I see IAA as engaging with both. Of course, we cannot forget that although we are creating an exciting, future, and I have pictures here of a flying future with autonomous taxis and drones, over a city. But then down at the right is a picture of Mumbai, which shows this large, populated, poor area bordering immediately against sort of a middle class and a more prosperous region. We have to, as we work on our AI, and I think, again, this will come up as Deborah talks about it, we have to think about our impacts at both domains. Issues of equity matter to us, and at Johns Hopkins, living in a city we do, in the neighborhoods we do, we see this every day. So who are the people who are in IAA now? Well, you're going to hear from the researchers on the talk. I wanted to show some of the resources, if you will, on the administrative and leadership side. Right across the top there, Tony DeBura and Kara Lapointe are co-directors. Tony of the Whiting School, Kara of the APL legs, if you will, of IAA. David Silberberg has been leading the research development. So those of you working on seed projects have been interacting, I think, with David on a regular basis. And I'd like to welcome Rama Chalapa to the team. Rama has just joined us as chief scientist for IAA. And we're very excited to have him with us. He's going to be helping shape those faculty hires we have as we move forward to the future, and interacting with all of you on the seed projects and the flagship projects as they're shaped up. Oh, and I should say here, critically, we have a great office. So the computer science department is working with us and providing support for those of you who are putting proposals. Those proposals, of course, are a key part of the F&A clawback, which ultimately feeds into IAA, which we then use to foster more IAA activity. Down there at the bottom, I'll just say that, you know, those you have, or in the middle, you have Laura Graham right in the center of this, and then Veronica Koch on the APL side. So Laura Graham is the administrative director on the Whiting School side. And then below Laura, just to give you a sense of our team, Alex Fink worked at APL and now works in the Whiting School side. And she's an example of the types of capabilities we want to cultivate in the IAA office as we develop a team who can move smoothly between the organizational boundaries. I think with that, I will stop by saying, you know, here are the seed research portfolio activities that we have that you'll be hearing about today. I won't dive into these. You'll be hearing from the individuals directly. I've left 15 minutes here for Q&A, and what I'd like to do at this point is I'll end the presentation, and hopefully David, Kara, and Tony, and Rama, and I know Rama had a conflict, so hopefully Rama's with us, can join me online here, and we can answer Q&A. I would ask that you put your question and answers in the Q&A function and not in the chat function. Although I'm sure that Veronica will be checking the chat function and moving things across just in case you put them in that filing. So stop share, and there we go. So let's see. I'm going to just sort of, I don't see any Q&As immediately, so I'll just sort of ask folks for comments. I'll come to David last, since David, you'll be hearing from David as we walk through the seed session. So Kara, do you have any comments that you might want to make here as we wait for Q&A?
Yeah, I just want to kind of build on what Jim said, is that, you know, we know there's a number of folks that are tuning in today that have been already involved with IAA projects. But for many of you, this may be kind of your first experience with IAA. And so really, IAA was an initiative that was started at APL and the Whiting School, but really incorporates more of the university as well. And the whole idea of it is to find better ways for us to come together between APL and the university to collaborate on this really important issue of assured autonomy, right? AI is being built in across our society, and we want to make sure as that's happening, that these technologies are safe, secure, reliable, they do what they're supposed to do. And so we have a lot of different exciting threads of what we're doing between the research, between some of the thought leadership efforts and other efforts. So there's a lot of ways to get involved. So please do, if you're interested in IAA, this is the first time you're interacting with us, get in touch, right? Because we'd love to collaborate with you and hear the kinds of things you're working on, because one of our roles is to be a connector of all of these things that are happening, because assured autonomy is very interdisciplinary. So a big piece of what we're doing is trying to connect folks across these disciplines, across the university. And I think we've got a couple questions in, Jim.
Yeah. So Tony, maybe you can just sort of briefly and make an introduction from the Whiting School side, and if you want to touch on either of those questions in your introductions, that'd be great.
Great. Thanks, Jim. Yes, welcome to everyone. This is a very exciting time. It's a very exciting time for the university, and it's a very exciting time for technology and AI. There are lots of things happening in application areas that we need to be paying attention to for societal benefit. And there are also very ambitious programs being launched at the national level to support our efforts. And so we really count on your support, working with us to identify those efforts and work together so that we can really become the preeminent organization addressing assured autonomy. Thank you.
I'm sorry, David. So we have a series of questions here popping up, and we'll go to those. I just want to give Rama a chance to say a few words. Rama, if you're online there.
Yeah, hi, can you hear me?
Can hear you.
Yes, thank you. As I said, I'm on 2 parallel Zoom calls. So I'm part of a member of the face recognition working group organized by the state senator, and we are working on a bill that is going to be presented so that, the privacy issue, the bias issue, they're all addressed and so forth. So it's not totally out of touch with what IAA wants to do, but I'm switching back and forth. So sorry about that. Thank you. And I came to Hopkins last year, and those of us who have worked in AI have seen AI spring, AI summers, and AI winters. I'm now thinking if you are not careful, then next AI winter may be lurking around the corner. There are serious things that we have to look at, robustness to adversarial attacks and the perceived bias and interpretability, all of those things, and assurance, right? So assurance comes with all of these things being taken care of. So this institute is very important. And if we do things right, I think we will have a big impact across the board, in transportation and medicine and surveillance and security, everything. So I'm happy to be part of the team, and I look forward to interacting with as many people as I can. Thank you very much.
Super. So I can see that, one of the questions here that's been upvoted are what are the biggest challenges in brokering a relationship between the university and APL? We just had a meeting on that yesterday. Kara has really been kind of, leading the charge together with Jim Broskow on this problem. I'll just comment that this was one of the things that attracted me to come to Johns Hopkins. To have sort of the intellectually vibrant, rich research campus, which is connected to the broad world of activity in AI, coupled to an organization like the Applied Physics Lab, which builds things and sends them to Pluto, and is connected to real world into the real world through system engineering and project management processes that are not things which are sustained on the academic side, I think is a synergy that allows a value flow both ways, right? Ideas, creativity, and people and education from the academic campus to Applied Physics Lab, and then from the Applied Physics Lab back to the academic side of things, a partner in turning our ideas into real systems and methods and tools that can be used in the broader community, as well as insights into what the real challenges are. I'm a big believer in use-inspired research, and I think that as you build things, you begin to realize that maybe what your idea of what the problem was is not the problem. That the real problems are, which come from application out there, are different problems, and I think that's very fertile ground to work for creating a vibrant program. And so Kara, I know you've been thinking about this for a long time. Do you want to touch on what you see as the biggest challenges?
Absolutely, right. And there's a lot of reasons, as Jim was laying out, for us to collaborate. And people are really excited about being able to collaborate more easily. But it can be a challenge, right? We have very different cultures between APL and the rest of the university. We have different business processes. We have different fiscal years even. So we've spent a lot of time focusing on how do we make all of the ways that we collaborate between APL and the rest of the university. How do we clarify? Because one of the things we find when we talk to people on both sides is there's some reticence to collaborate because it's just people aren't necessarily clear on how you do it and what the policies are. And then in some cases, we're identifying places where we can streamline things, right? Just to make it easier. Because at the end of the day, we don't want the challenges of collaboration to be a barrier to us being able to work together. Because the power of IAA and what we're doing is that we have that connection where we go all the way from foundational research all the way through application and impact. Right. And it's a two-way street, right? The use-inspired research is important, but then also having the full depth of kind of the S&T research that, and in combination with more R&D that is done over on the APL side. So we're working on clarifying existing policies, streamlining where necessary, And the university is really looking at this as us kind of trailblazing to be able to help other collaborations between APL and the rest of the university. So if you have thoughts on that, please feel free to reach out. We've been kind of collecting lots of we've had a lot of discussions on what the specific challenges are. We've identified a whole number of them, but if you have lessons learned of successes or challenges, please reach out because that'll add to the conversation.
So we have another question here, which is, it's really kind of a question about the business model, I think, of IAA. So can I talk about the IAA objectives with respect to funding research, attracting grants and sponsors, and other sources of external funding for research? So this is part of my learning curve here as I arrived. The business models for IAA are different, right, on the APL side and on the academic campus side. On the academic campus side, well, actually, from the president's office, what happened was you had a big infusion of seed funding, which was very heavily used for the seed projects. It's also used for the flagship projects, also used to renovate STEEF. So we actually have so we all have a place to sit. So that idea of funding the seed projects, which really started, I mean, you all were engaged almost 2 years ago, I think, at the beginning of this process, served a couple of different objectives. One was to foster these teams between APL and the academic campuses. The second was to build sort of a critical mass of individuals engaged in and thinking about assurance. And finally, you all are intended to be the seeds for externally funded activities. So the business model on the academic side, particularly the Whiting School side, is that as that research volume picks up, right, as you all apply for research activities, and there's currently a large NSF AI initiative, which has a trustworthy AI component to it, which we're very focused on thinking about how Johns Hopkins should sort of frame its response to that. And so those are the types of things we want to see and we want to foster and we want to have go through. And then what those do is they go through, there's an F&A clawback. So a certain fraction of the overhead actually comes back to the institute. This is true broadly of all of the institutes and centers inside of the Whiting School. It doesn't cost the departments anything, but what it does do is it gives you sort of the ability to invest in people like Alex Fink and so on, who will provide the support infrastructure, as well as potentially for seed activities. Perhaps hiring a postdoc or funding some seed or exploratory activity. So those are kind of the classic methods inside of Johns Hopkins. Another piece that I'm very eager to develop, which has not been a model which has been used much here, is the industry consortium model. And so I have some pretty strong ideas about how I'd like to go about building up an industry consortium, which would bring in money, but also engage us intellectually to organizations which oftentimes are in the forefront of AI. So that's kind of why I ended sort of my talk with that discussion. Let's see, Discovery Grant Program. We're kind of coming down here. We got a couple of minutes left. So Kara, do you want to touch on that?
Yeah, so I guess the question is, how does IA differ from the Discovery Grant Program to link parts of the full Hopkins system? And can you overlap the two? They're complementary. We actually are encouraging folks who are involved in IA-related research to also apply for the Discovery Grant Program. That's an ongoing grant program at the university that has also been very successful in linking researchers. So I'd say they're complementary. Our seed funding is really to drive external funded research as well, right? It's kind of that initial priming the pump. So I think that's a little bit of a difference, whereas the Discovery Grant Program is ongoing.
So I think we'll take maybe one more question here. I see two questions from Reed Young, both of which revolve around the future of IAA. I think what we all want is an intellectually vibrant environment, and we would kind of measure that a lot of times in the classical ways, right? Are we publishing? Are our publications cited? But we would also see it by impact, right? From a technologist perspective, it's kind of how have you affected people's lives? And so we're developing the tools and methodologies that we hope will help people make sure that the AI that they develop or the autonomous systems they develop really work. So as we start seeing adoption of our technologies, tools, capabilities out there, that'll be a measure of impact. I also think there's an opportunity to really sort of bring our educational programs and merge in a way our activities between APL and the academic side. We've been having a lot of discussion of this internally. Where I came from last, Woods Hole had something called the Joint Program with MIT, which, to put it bluntly, trained leaders in the field. And we would like to train leaders in the assurance space here. So I think what we haven't touched on much is the security aspects of it, which of course Tony has led for 20 years now. And so I think maybe what I'll do here is before we break to actually getting to the real stuff, Tony, just sort of give the floor to you and see if there's any comments you want here to touch on to bring this part of it to conclusion.
Yeah, thanks, Jim. One thing I want to stress is that our IAA community is not defined solely by the initial round of seed funding projects. We're looking across the university and beyond for worthwhile, relevant, leading edge research projects that we can engage in and support. And also, we're really excited about the prospect of defining and implementing flagship projects where researchers and engineers can converge from different areas and build systems that prove out the tools and methodologies of assurance that we've developed within the IAA community, and also identify new problem areas, new challenges that will lead to additional research. So those are a preview of things to come.
Terrific. Well, with that, maybe we should end our 30-minute preamble and get to the main to the meat of the event. Over to you, David.
Hi. So now you'll hear presentations about each one of the seedling funding activities. They're quite exciting. They actually span a broad spectrum of some of the most difficult problems in assured autonomy. As you see that they fall into roughly 4 different categories listed at the bottom: safe and reliable systems, secure and resilient systems, seamlessly integrated systems, and beneficial and ethical systems. And that's one way of slicing it. There are a lot of ways to slice it. However, they're all interesting activities, and I hope you'll enjoy their presentations. Afterwards, there'll be a breakout session where you can meet with each of the PIs and have more in-depth discussions. And if you want to get involved, want to work with the teams, we'd be thrilled to have you as part of the team. So over to the presentations of the research portfolio.
My name is Chen-Ming Huang. I'm an assistant professor in Department of Computer Science. Today, I want to talk to you about a project that Yizhen Wang at APL and a few other colleagues have been working on in the past couple of years, supported by IAA. So this project is socially aware robot navigation in human environments. To start off, I want to just to give you a sense of where we are in terms of robotic assistance, mobile assistance. So in the past couple of years, in the past few years, more and more companies are developing and employing mobile robots to offer their services to customers. Even governments doing this. Just last year, Japan Post Office rolled out a mobile robot that help deliver mails to their citizens, right? So, and I think part of this is driven by pandemic, right? So we see more and more robotics assistants actually coming out to the road. But this is not just happening in the outdoor environment, but also in indoor environments. I'm just going to show you two videos, and these two are coming from one of my students who went back to South Korea this past summer, just a couple months ago, and took these two videos. One is in the restaurant, the other one's the airport. So let's take a look. So what you're seeing right now is the kitchen staff in the kitchen, put the dishes on the robot, do some setups. The robot navigates to the receiving window. And it navigates in a crowded environment. People sort of adapt how the robot operates and move in the environment. But this is happening right now in South Korea. On the right, it's again a mobile robot in the airport where it takes your suitcase, your luggage, and then it can navigate to either a specific gate or follow you. So this just show you the kind of robotic assistance that a lot of places are using right now. And one of the element is operating in the human environment, right? Either in the very crowded restaurant or less crowded airport, but still it's a human environment. So this project is really, motivated by part of this is really looking at robot navigation, considering complex human social behaviors. And we believe that this is very important in order to achieve assured autonomy toward building a safe, productive human-robot ecosystems, which arguably I think we are all on the path toward this vision. But if you think about this, right, this is not a new problem. Like robot navigating in human environments is not a new problem, but it's a very complex situation to operate in, right? So thinking about human social norms, human behaviors, just like a lot of complexities, right? You need to consider various parameters such as how to approach a person, what's the approach angle, what's the approach velocity, do we need to do any social interactions, right? Basic making eye contact. Part of this depends on the design of the robot. How do we maintain the necessary social distance to avoid basic discomfort? How do we share space following certain social norms, right? So in the context of the US society, will be, for example, navigating in a hallway, you want to navigate to the right side. And there are more, right? One of the things that we're looking at in this project particularly is to consider social groups. A lot of prior work in this space essentially treat pedestrians, treat individuals as individual identity as opposed to social groups. But the fact is, when people navigate in together in the environments, people naturally navigate in a group, right? There's actually a research showing that about 70% of the time people actually walk around as a group, right? So this means that treating individual pedestrian as individual entity is probably not the most effective way to approach robot navigation in the human environment. So the potential downside of this is that robot might just cut through social group, which I think arguably is a very rude and probably not appropriate way. So how do we go about doing this? So the first step we did is to build a simulation environment that allowed us to do this, right? So these are the two, the animations show you the kind of current state. A lot of simulators out there, right? They simulate pedestrian, they simulate agents as an individual entity and do not consider the group concept. And consequently, this doesn't support a lot of learning around the group concept. So our first step is to build these software packages that allow us to simulate group behaviors. And we integrate that software plugin to a crowd simulation environment so that we can do a lot of training, right? So naturally, the next step for us is to do a learning-based approach toward learning this group concept. So on the left-hand side, we show you this is probably the most common approach to this is to learn individual level behavior, right? Try to minimize individual discomfort. Versus in the middle is our approach is trying to capture this group concept. So the way we do it is in our reinforcement learning framework, we add a specific term, reward term for group concept, and we try to maximize that. So just show you one simulation example, right? So on the left is the baseline, on the right is our approach, right? You'll see on the left, the robot try to cut through the group, get to the goal as efficient as possible. Versus on the right, the robot sort of avoid the group sort of congregation. We did a bit more thorough analysis compared to a few different baselines and look at different metrics. Today, I just want to highlight three sort of aspects, right? Three columns. The first one is pedestrian collision, right? Our approach, the group aware one, actually had fewer collision with pedestrians compared to others. The second aspect I want to highlight is the middle one, the mean pedestrian velocity, right? So this essentially is an indicator of the robot's behavior impact on the pedestrian, right? So if the pedestrian velocity still continue to be high, that means that their behavior is less impacted by the robot's behavior, which is what we've shown here. And the last one is a group intersections, right? So that's the thing we were talking about, like we don't want the robot to cut through the group when they are actually a group of people, right? So our approach, which is not surprising because we optimizing for that, right? So our approach actually had fewer intersections with a group of pedestrians. So if you're interested in this, I'll be happy to talk more offline. We have a paper under review right now on this group aware work. But next, I just want to show you that we ported this simulation results to a physical robot, right? So we did this demonstration at APL with a spot robot. So the first video I'm going to show you is a robot and a group of two. So here the robot recognized it's a group of two, try to avoid cutting through it and then bypass it. The second video is the same idea, a group of two, but coming from a different angle, right? So the robot works toward the goal, recognize there are people coming for it, avoid it. The next one I'll show you is two groups. So we have two groups of people coming toward the robot also passing, trying to get the goal, and for the robot to not cut the individual group, but just go in the middle. Yeah, so over the past couple of years, we have built some research infrastructure for this. We have a reinforcement learning based environments to support learning social behaviors. We explore a range of metrics to assess and evaluate socially appropriate behavior for the robot. We are able to ported our results to the physical robots for demonstration. And what we're working right now is a longer term deployment. So I'm running out of time. So we have a new mobile manipulator coming, and then so we are just to explore what kind of assistance we can have for the robot to do. All right, so I'm happy to talk now. There are a few directions that we're exploring. One of the things is to this is a joint exploration with Ross Taylor. We're looking at this Johns Hopkins central stereo processing. We're thinking about how to integrate mobile assistance into their workflow. Happy to talk more offline if you're interested in this. I'm a bit over time, but thank you very much for your attention.
Good morning. Welcome to the presentation of Assured Autonomous Vehicle Policy. My name is Todd Chen. I'm a PhD candidate at Whitening School of Engineering from the Johns Hopkins University. Today, I will share our works on Assured AV policy. Our goal is to help the design of AV deployment policy that can generate social benefits. The challenges are that people do not trust AVs very much nowadays because of concerns about safety. Also, not many people have real experience with AVs. Public has not decided to totally adopt AVs yet. We believe that assured technology is not just safe and individually beneficial, but that is socially beneficial and therefore worthy of public investment. Hence, we need to deal with this problem systematically and comprehensively. This project involves multiple schools and researchers from different backgrounds, including Institute for Assured Autonomy, Whitening School of Engineering, and Bloomberg School of Public Health. We developed the framework that integrates simulation validation and public survey to inform the policymaking processes. So we can achieve assured AV deployment that is preferred by public and validated by simulation. In the following presentation, I will first lay out our iterative study design and then share ongoing work in AV simulation and public opinion surveys. This flowchart shows the approach of our policymaking framework. The novelty is that the processes are iterative. The policies will be adjusted and refined once informed by the public opinion gathered from the surveys and the validation of traffic simulation scenarios. We focus on policies that could use AVs to help those with limited mobility and accessibility to provide social benefits. This is different from a market-driven deployment, which might lead to unintended impacts. We met with government officials to discuss and understand the pressing issues that needed to be solved. This picture was our meeting with the officials from South Baltimore, and I was presenting how our work could improve the problems. Since the public surveys are undergoing, these meetings help us to develop simulation and analysis of improving food desert in South Baltimore, which is a demonstration of our framework today. This is Cherry Hill in South Baltimore, a typical food desert area. The closest grocery store is on the left, far from the residential area on the right. Many households living here have no access to a car, so they rely heavily on public buses. However, the bus service is limited because of inconvenient bus lines and sparse bus schedules. So it is not convenient for the residents to go grocery shopping and get nutritious food. We built 3 simulation scenarios for deploying of AVs to improve the healthy food access. First is the AV ride sharing, where the AVs operate like taxis and transport people to the grocery store as the orange route. Second is that the AVs travel as looping shuttles on the blue route. In this way, the AVs are facilitating the current public transit system but not replacing them. Third policy is for AVs to deliver food to the local convenience store, pointed out by the yellow arrows, for people to pick up. With the simulations, we can identify the improvement and unexpected consequences in each scenarios. For example, here are the heat maps of travel time in baseline and AV looping shuttle scenario. The maps shows that travel time decreases for most people, but some are not benefited much. Moreover, we can assess the change of travel behaviors from the simulation results. Here are the pie charts showing the time spending on different travel behaviors. In the AV loop shuttle scenario, we can observe that high percentage of people did use AV shuttles instead of only riding buses. In addition to simulation, we are developing surveys to gather public opinion on AVs. This survey is ongoing, with 28 questions, including baseline view of AVs and scenario deployment questions. We are expecting to have 2,000 adults for the sample. The survey aims at assessing how the opinion changes if social benefit is informed. Here is a sample question of testing baseline attitudes towards AVs. We ask how comfortable the subject will be when riding in a fully self-driving car. In the later part of survey, we provide background information, such as the potential of AVs to provide social benefits for people in need, like improved mobility of people with limited income, vision impaired, and elderly population. Then, we can test if their attitudes change when considering social benefits. This question is asking if the subject support using AVs to provide transportation to the elderly. To conclude our work, assured policy requires applicable technology and public trust. Our traffic simulation can validate and provide insights for AV deployment and support the design of survey question. The policymaking process would be iterative and informed with simulation and public opinion to achieve resilience and assuredness. Thank you.
Hi, I'm Phil Berliner, and with my collaborator, Professor Yingzi Chao at Computer Science Department, we've been working on issues of AI privacy and fairness, along with other collaborators at the Applied Physics Lab, University of Maryland, Queen's University, Duke University, as well as the Johns Hopkins School of Medicine. So among the many issues that affect assured and responsible AI, fairness and privacy and robustness as well stand as some of the most important in terms of being able to deploy this AI in production environments. And what's interesting is that privacy and fairness share many traits. They share many common causes as well as have many common remediation. So there are different use cases that that are affected by fairness and privacy. Some of the examples are depicted here and involve action recognition, medical analytics, and face recognition, as well as being able to predict recidivism, for example. We are specifically vested in the use cases of medicine, as well as and diagnostics, as well as being able to do face analytics. And so what does it mean to be fair and private? Essentially, fairness means that the AI should not discriminate. There should be some parity of opportunity. There should be a same diagnostic accuracy with regard to protected factors such as gender, race, and age. And vis-a-vis privacy, it means that the AI should not leak private information that will, for example, invalidate HIPAA. So I'm going to talk about fairness first, and Yingzi will talk about privacy later on. But vis-a-vis fairness, there's many different possible objectives and nomenclature and definition. And I'm giving one example here, equality of odds, but there's many different possible definition of fairness, and this correspond to different settings and different type of policies. But equality of odds essentially state that if you have a predictor, which predicts P of y hat, and a condition on the actual underlying y, and y hat represents the presence of diabetic retinopathy, for example, or cancer. And then this condition on the protected factor S, that this in fact is independent of S, okay? And so in general, many times, you have a Tiemann variation on this sort of definition of fairness, which states some sort of condition of independence. And this condition here directly translates into a condition of equal performance vis-a-vis sensitivity and specificity of probability of detection, probability of false alarm, that this be the same, that the performance be the same irrespective of the protected attribute. And what's interesting about this definition here is that if you substitute S being a protected factor as S being a private factor, then here you have a common definition that talks about fairness, but also talks about one aspect of privacy, which is privacy vis-a-vis not revealing private attributes. So let's talk about approaches to making models more fair. So if models consist of data, which is used to train some models for which we create some prediction then at inference time, then there are three types of intervention, broadly speaking, and those are intervention both for privacy as well as debiasing as well as fairness. So these are either pre-processing intervention that modify the data, or they are in-processing intervention which intervene the model, modify the model, or post-processing intervention which do some sort of alteration of the softmax output or the logics themselves. And I'm going to show you two examples of intervention that consist of pre-processing and in-processing. So oftentimes, fairness is affected by the fact that we have unbalanced data, we have missing data. And one thing we can do to reestablish balance is generate more data. And because it's hard sometimes to go back and sample more data, we have used the generative method and different flavors of generative method involving information theory principle to be able to generate more data that was perhaps missing at the time of training of the data set. And so therefore, we do some sort of intelligent augmentation with this additional data. And what I'm showing here is the example of modifying and controlling the attributes of data so that you can control, for example, the skin factor and the orientation of the face. And you can do likewise for medical data. And this can be done using those GANs, this information theoretic GAN, or they can be used by doing some sort of latent space modification, which leads to the generation of the required or the requisite image markers that, for example, would translate some exemplars of African-American retina into similar exemplars where nothing else is modified, but some realistic image marker for the disease are being created. And by doing this sort of manipulation and augmentation, we can show that, for example, in the case of medical diagnostics, and in this particular case of diabetic retinopathy, that it's possible to significantly reduce the accuracy gap, which is the accuracy difference between population of darker skin individuals and lighter skin individuals, while mostly maintaining the overall accuracy. And this is a theme that comes back often because when you're intervening, you run the risk of lowering the overall utility and accuracy of the model. And so therefore the name of the game in terms of fairness is, and as well as privacy, and it's another touch point, is to maintain the utility of the method while increasing the fairness and while decreasing the accuracy gap. So here's an example of another type of intervention on the model itself. And essentially what's being done here on the right is a depiction of, we have X, an input image, which is going through an encoder, which leads to a representation. And from this representation, then we can predict some sort of task, such as, is there cancer? Is there a skin lesion or whatnot? But what's done here is that the addition of an adversarial player, and the role of this adversarial player is in fact to disallow the possibility of backing out the value of the sensitive attribute, okay? And so therefore, like at the end of the day, what we're able to do is to do accurate predictions, so maintaining the utility while diminishing the likelihood that this prediction be done with the knowledge of the protected attributes. And this can be combined with the preprocessing methods. And when applied to the problem of face analytics, for example, predicting age, it can be shown that the combination of those two methods, the preprocessing and the in-processing, leads to best of class results. And these results can be measured vis-a-vis utility and fairness separately, or using joint metrics of utility and fairness. And this is shown here. And for further reading, I'm giving some additional reference here, and I'm gonna now pass on the baton to my colleague, Professor Yingzi Chao.
So now we're transitioning to Yingji's talk on privacy. It'll be up momentarily.
Hello, this is Yingzhi. I'm going to talk about privacy in artificial intelligence. So as we all know, like privacy is very important. So in machine learning, it's being used in different areas such as medical diagnosis, language recognition, self-driving car, and social media, and all those machine learning use cases. There are some privacy being involved, like patient medical records, like your income tax, like your locations, and also like how you behave on social media. So because of the privacy, machine learning is very important. We target a specific part of privacy in machine learning. So that is, we try to look at the attack called membership interference attack. What it does is that when it looks at a training data, and then it tries to predict that a given input data belongs to the training data, and then it will infer this information. So specifically, the state-of-the-art machine learning and the membership interference attack does is that it given a target model and given a query data, it's going to acquire a target model and obtain a prediction score. And then after that, it also train a shadow model based on local data. And based on local data result, it's going to train another attack model. And then the output from the target model going to be fed into the attack model, and then we'll get a result of whether it's a member or non-member. So the question we have is, what if the shadow model is not like the target model? So we look at this table, we'll see that if the target model is resting at 50, but the shadow model is like CNN or VGG, and the attack F1 score actually decrease a lot. So that's why we decide to give up the shadow model. And what we do is we propose a new attack called blind MI. The idea is transfer the target data set to a non-member data set and then feed into target model and get a prediction. And then after that, we're going to compare a given data with the non-member data and then decide whether it's a member or non-member. So there's no shadow model being involved. Some variations involving the blind MI1 class, with one class was VMs, also a blind MI diff, which is a novel approach to use differential comparisons that differentially move samples away from each other and decide what is a member or non-member. And then after that, we also propose things related to how to defend against membership influence attack. The high-level idea is to use a GAN to generate synthetic data samples and then mix synthetic data samples with raw data samples into a diagnosis modeler. And then after that, this will be robust against black box attack and the gray box attack.
Okay. Up next is the Radix project, Runtime Assurance of Distributed Intelligent Control Systems. This will be presented by Yair Amir and Tamim Sukar.
Hello, my name is Brian Wheatman, and today I'm going to talk about assuring autonomous system by using Radix, which is runtime assurance for distributed intelligent control systems. So first, why do we want to assure AI systems? See, AI systems are great at what they do. However, normally what they are trained for is the average case, the common case. And what this means is while they have very good performance here, they'll still have some edge cases which they are unable to handle. And in critical systems, these edge cases can lead to total system failure. Ideally, we would have some sort of system that allows us to get the benefits of AI in the common case without paying for the cost of these edge cases. To do this, we introduce Radix, which combines an invariant-based black box monitor and a white box monitor that looks into the state of the AI subsystem to both ensure correctness and maintain good performance. So first, what is black box monitoring? Black box monitoring is a standard approach for creating dependable systems. These systems work roughly as followed. You have some piece of critical infrastructure from which you can collect state. This state is sent to two different controllers, one which you know is good, which will always do a correct answer, another which is allowed to use AI, which may perform better in the average case. However, in some cases, we know it may perform much worse and fail. And lastly, some form of black box monitor. This black box monitor is able to tell how close is the system overall to failure. So when the system is close to some failure region, it will take the decision from the safe controller and allow it to run the system. However, when the system is far from failure, then we can use the AI controller. And as long as the AI controller is reasonable, we should stay reasonably far away from failure, and thus the AI controller can control the system most of the time. We can think of this as like a bullseye. Whenever the system is in the green or safe state, the AI controller can run the system. However, when we hit the red region, we are getting close to the black or failure region. And so we switch control to the safe controller, which has some amount of time, the width of the red region, to rescue the system before we reach the failure region. However, this approach has a few limitations. The first is, when will you switch back? It's clear as soon as we hit the red region, we need to switch to the safe controller to ensure correctness. However, if we switch back to the AI controller as soon as we hit the green region, and the state of the world is the same as it was before, we will immediately re-enter the red region and begin oscillating between the two controllers. And while we will maintain correctness and not reach the failure region, performance will suffer during this time. To help eliminate this, we add a white box monitor to develop the full Radix approach. Here, the white box monitor is able to look into the AI controller and determine how confident it is in its decision. This helps both with switching to and from the safe controller. You see, if the AI controller is not very confident, in its decision, then we'd most likely want to switch to the safe controller sooner, and vice versa if it is very confident. And similarly on the switching back. We know we don't want to switch back to the AI controller if it's not going to be very confident. We can also think of the decision of the radix system in our bullseye approach, with adding this yellow wing between the green and red regions. The red region still needs to be the same size to ensure correctness by giving the safe controller enough time to rescue the system. When we are in the yellow region, the system is allowed to, but not required, to switch to the safe controller. If the white box monitor says the AI controller is very confident in its decision, we can still go up to the red region before we switch to the safe controller. But if instead the white box monitor says we are not very confident, we can switch as soon as we enter the yellow region. This can help limit the oscillation we talked about earlier and also increase the performance. Now we can see some of radix's limitations. The first is that we need some safe controller that will always be able to rescue the system from any state. The system also needs to exhibit a slow degradation towards failure. We can't have any single bad decision lead to failure, else, to ensure correctness, radix would have to always run the safe controller. To evaluate radix, we made a small simulation of a traffic grid with 4 intersections. The goal of the AI is to control the lights to maximize the average speed of all the cars. We trained the system on a rate of 500 vehicles per hour on all edges. We found a failure case, which the AI is unable to handle, with 100 vehicles per hour on all but one edge, which still has 500 vehicles per hour on it. We find this interesting since it is purely less cars than the train scenario, and thus it feels like it should be easier. We evaluate 4 different models. The first is a safe algorithm. The second is an AI algorithm with no monitoring. The third is just using a black box monitor. And the last is using a full radix. We evaluate this in 3 different time regions. At the first stage, up until about 10,000 time steps, the simulation is running at a scenario that the AI trained for. Then, in the middle region, for about 3,000 time steps, the simulation introduces a scenario which the AI was not trained for. And at the end, for the remaining time, the AI goes back to the trained scenario. What we see is that during the trained scenario, the AI is, as expected, able to perform a fair amount better than the safe algorithm. However, during the untrained or the anomalous scenario, all AI systems perform poorly. However, the ones with monitoring are able to detect the failure and stop us from crashing too much. Furthermore, we see the black box does, as hypothesized, have some oscillation between the 2 controllers, which does lead to a little worse performance than the radix system. So, altogether, we do find that radix was able to help us ensure system correctness and maintain reasonably good performance. We find overall radix does perform the best, and in segments 1 and 3 has the best overall time, and in segment 2, during the anomalous scenario, is able to perform better than the other approaches and get reasonably close to the safe controller in that scenario. Future work involves running more complicated scenarios and testing different styles of white box monitoring to better predict when the system will fail.
I will now discuss applications of radix to a power grid application. Our goal is to introduce AI to a power grid in order to make energy consumption more efficient and to use radix to keep the system stable. We model a small neighborhood grid in which alternative energy sources are available alongside traditional electricity generation. We would like to add intelligence to the homes in this neighborhood so that they can respond dynamically to the price incentives. These price incentives are provided by an intelligent utility company in order to reduce differences in electrical supply and demand. Our primary research question is, if the homes and utility company are all using AI, can we design a system monitor to keep the grid stable? Currently, we have implemented an AI for the utility company using deep reinforcement learning, which learns to set prices dynamically. You can see the prices over the course of a day in the top plot. Differences between electricity supply and consumer demand, which is shown in the bottom plot, is called residual power. Our AI learns to keep residual power close to zero by altering the price of electricity. The next step is to add more intelligence to the consumers so that they can also optimize their behavior and see what instabilities may occur in this system. Can we prevent these instabilities with a system monitor? Here are some more details on some monitoring approaches. The goal of the monitor is to determine if an AI trained with deep reinforcement learning is uncertain about its own behavior. Specifically, we want to detect situations that are different from what the AI encountered during training. We are investigating a technique called random network distillation. Here we create a random network that operates on training states, and then we train a second network to mimic the outputs of the first network. If we encounter a brand new state, we will not know what the random network will output, and therefore we will not be able to mimic the initial network. The difference between the outputs of the two networks tells us our uncertainty. In the plot, we see this method used to measure uncertainty in a grid world. The agent was trained in the middle and shows high uncertainty as we move outside of the training area.
Next up will be Assuring Autonomous Airspace Operations with Lanier Watkins and Lewis Whitcomb.
Welcome to the IAA Knowledge Sharing event, and welcome to the presentation entitled Assuring Autonomous Airspace Operations. My name is Lanier Watkins. I am the APL PI for this project, and my colleague Lewis Whitcomb is the Whiting School of Engineering PI. This slide depicts the combined team for this project. The aerial landscape is quickly changing. The FAA predicts that the commercial drone market could triple in size in just a few years. The writing is most definitely on the wall as several companies launch their autonomous drone services. There have been several predictions about the state of affairs of the future drone market. One prediction is that by 2035, the number of drone airspace operations could be as much as 65,000. As a baseline, the U.S. busiest airports handle less than 300 operations per hour. The proposed solution is Unmanned Aircraft System Traffic Management, or UTM. UTM is a conceptual complex interaction between operators that want to provide services to their customers and the UTM system itself. However, to address the predicted scale, UTM must likely leverage autonomy to produce safety in high-density drone airspace. UTM is in its conceptual phase and generally lays out a plan for UAS to be safely managed without routine manual intervention. However, there are human-in-the-loop conceptual processes. Assuming UTM is successful, there are plans to extend this concept to higher airspace to meet the needs of proposed services such as advanced air mobility. Pieces of UTM are currently being studied by the U.S. government and industry partners. Our approach is to replace these human-in-the-loop conceptual processes with autonomy. In doing this, we simulate operators submitting plans to the UTM system for strategic and tactical deconfliction of operator flight plans. Then operators are informed of their new deconflicted flight plans. Autonomous versions of the conceptual processes within the red box is what we are simulating. And now my colleague will speak to insights gained from year one Whiting School of Engineering work.
The problem that we are addressing is how to navigate on uninhabited automated aircraft effectively in the presence of navigation sensor noise. In year one, we implemented a multiplicative extended Kalman filter that can run on each of the simulated UASs in our simulation environment. And these extended Kalman filters take simulated sensor measurements from the global positioning system on board the aircraft and the aircraft's inertial measurement unit, or IMU, which measures heading and attitude, and it estimates the vehicle's 6 degree of freedom state, position, and velocity. It reports this navigation estimate as well as uncertainty estimates via a navigation certificate to the centralized USS. And the centralized USS also runs its own tracking system, which is a centralized version of the multiplicative extended Kalman filter, and can thus track any number of simulated aircraft. This slide shows the structure of the multiplicative extended Kalman filter, which uses as inputs data from navigation performance certificates and navigation sensor values from the global positioning system and onboard inertial measurement unit. It then estimates the vehicle state and outputs estimates of the vehicle position, velocity, attitude, and angular rate, as well as covariances or estimates of the certainty of those estimates. This is a sample XY navigation track of a scenario in which 3 UASs performed 3 independent missions. The blobs that you see on the right are obstacles with safety margins around them. This slide shows a close-up of the vehicle true track, which is the finely dotted line, the GPS fixes, which are the widely spaced dots, and the extended Kalman filters state estimate, which are the dashed line. In summary, we've implemented and tested a decentralized and centralized extended Kalman filter for estimating the aircraft state in the presence of navigation uncertainties due to sensor noise, and we're in the process of running larger scale simulations to understand how navigation errors affect the safety and efficiency of multi-aircraft operations.
And now I will speak to insights gained from year one APO work. The work that we have done is a Monte Carlo simulation with tunable and exchangeable parameters such as number of UAS, probability of rogue drone behavior, strategic deconfliction algorithms, technical algorithms, and others. Also, there are static and dynamic obstacles and safety and performance metrics. Here I will discuss highlights from our publication entitled An Investigative Study into an Autonomous UAS Traffic Management System for Congested Airspace. In this paper, we evaluate a portion of the UTM ConOps using a set of autonomous algorithms for flight plan deconfliction. We observed that given a mix of different strategic and tactical deconfliction algorithms in congested airspace, the number of dynamic near-mid-air collisions were extremely high when no safety algorithms were used. And it increased drastically as congestion was increased. Using congestion avoidance alone resulted in some decrease in dynamic static near-mid-air collisions, but once congestion reached a critical point, the collision avoidance algorithm no longer had the space necessary to make emergency maneuvers without colliding with other UAS. By using the Stratway scheduler alone, collisions were reduced to a fraction of the number than with just the collision avoidance algorithm alone. The trends for safety established in the previous slide were unaffected by rogue behavior, even with almost all of the UAS exhibiting rogue behavior. We define rogue behavior as UAS deviating plus or minus 1,000 meters from deconflicted flight plans. Thus, congestion is a larger hindrance to safety than rogue behavior. Next, I will discuss highlights from our publication entitled Assuring Autonomous UAS Traffic Management System Using Explainable Fuzzy Logic Black Box Monitoring. In this paper, we use a fuzzy inference system to evaluate the decisions of strategic deconfliction algorithms in an autonomous UTM simulation. The fuzzy inference system performs black box monitoring on the autonomous UTM system we described in the previous paper, and risk levels are assigned based on the autonomous UTM system's inputs and outputs. Based on our results, our fuzzy inference system is able to properly assign risks for safe and unsafe airspace. We define safe airspace as scenarios where strategic deconfliction is used, and unsafe airspace are scenarios where strategic deconfliction is not used. Explainability of the assigned risk is accomplished via the analysis of fired rules. These rules are here at the top. These fired rules reveal the met if-then conditions that lead to the risk level assignments. Our current Year 2 highlights include a Best Paper Award for FAA-focused A30 work published at the 2021 Air Traffic Management Applied Research Conference. Also, we received an invite to present at the Business of Automated Mobility Flight Path to UAM conference sponsored by SAE International and the Association for Unmanned Vehicle Systems International. We're currently working on a convergence paper between the APL and Whiting School of Engineering work for a journal, which is the computer, IEEE The Computer, which is the flagship publication for IEEE. So far, we have produced 3 publications and a patent disclosure is pending. Thank you for your time. Please let us know if you have any questions.
Thank you, Lanier and Lewis. Up next is Physical Domain Adversarial Machine Learning for Visual Object Recognition. This is joint work among Alan Ewell, Yinqi Zhao, and Phil Berlina. The presentation will be up shortly. If anybody has questions, they're welcome to enter them into the Q&A box, and there will be a live breakout session, virtual live breakout session at the end of these presentations.
Looks like we're working through a little bit of a file issue. So just to give a bit more information about the breakout session at 12:30, at 12:10, that's going to be from 12:10 to 12:30, and we are going to have a separate Zoom link. I'll put it in the chat so that everyone can join. That'll just give you an opportunity to talk to all of the PIs one-on-one and get a little bit back and forth with them and for them to connect with you for future collaboration. It looks like we're still having a bit of an issue with this recording. If it's all right, I think we can just jump to the next one and come back to this one before we end.
Okay, so the next recording is risk-sensitive adversarial learning for autonomous systems. So, so Brian Gardner and also Raman Arora. I hope you enjoy this presentation, and hopefully we'll be back to the other presentation when the technical issues have been worked out.
Gardner, and I'm excited to tell you about risk-sensitive adversarial learning for autonomous systems. Here's a quick snapshot of our joint JHU APL team. Raman Arora is our JHU co-PI. And this project is about reinforcement learning. Reinforcement learning is a type of machine learning where an agent learns by interacting with its environment and observing the results. It's resulted in numerous famous successes, such as Superhuman Go, which had been a long-standing AI challenge, various self-driving car successes, Superhuman StarCraft, and many others. At the same time, these successes happen in limited constrained environments. We'd like to give you a quick taste of some of the things we're looking at to bring RL closer to the real world, safe and effective, and hope you'll come talk to us if you're interested afterwards. So the first thing I'd like to talk about is risk-sensitive learning. Risk arises in RL settings due to uncertainty about possible future outcomes. And traditional reinforcement learning optimizes for the best average outcome. And the underlying math is built on this assumption. This can be a problem if, for example, an agent gets me to work with a reward based on time, and one day we have awful traffic and I'm really late, and the next day we just have really incredible traffic and somehow I get to work much faster than normal, and these two could average each other out when in fact what I may have wanted was to be on time both days, even if it was a little bit slower. And so our approach here, and credit to Jared Markowitz, as he's the one driving this work, is to develop a new RL algorithm to enable selection of different risk profiles. In particular, we want to allow users to weight experiences differently with respect to the distribution of outcomes. So for example, someone may want to put the most weight on the worst cases to try to minimize those. And so we've run this on 6 different environments and had success in all of them. Let me give you just kind of a quick sense with an example here. Ours is the one in yellow compared to states of the art. And we can see that the rewards are better as training goes on. The costs, which in this case are undesirable collisions, are much lower. And if we look at the distribution of rewards, we can see that it is much better. And this was really a surprising result of this work. Our original hypothesis was that we could tighten this distribution, remove some of the negative outliers, but this was really an exciting result that it turned out that actually emphasizing those more challenging scenarios actually improved the learning overall. And let me show an example here. This is CrowdSim. This agent has been trained to make it to the goal without colliding with these pedestrians, optimized for the average reward. But we can see it does collide. And then if we look at the case where it's optimized for the risk-sensitive measure, the agent makes it to the goal. The next thing I'd like to talk about is adversarial learning. The problem we're interested in here is that agents are likely to encounter unexpected environmental conditions. So for example, if they're deployed in the real world, it's almost certainly going to be somewhat different at some times, at least, than simulation. But training typically happens in simulation for practical reasons. So the approach we're taking here is to train the environment to behave adversarially and allow it to interfere with the agent. And to be clear, others have introduced this general idea, and we're working to improve it in several ways. And so let me illustrate a benefit of this approach. So what we have here, this is a safety gym environment. We're using it because it's widely accepted among the research community. And the idea here is this red agent wants to try to get to these gray outline goals without hitting the purple and blue obstacles. And we can see that in the nominal conditions, it's quite competent at doing this. It's not always perfect, but it's quite competent. Now let's take that exact same controller that we trained inside the last one, but let's pretend we deploy it in the real world, and the motor gain is a little bit less than we expected, and the turn gear is a little bit higher. And now what we'll see happens is first the agent just spins. I'm actually going to just skip ahead. So when it's done spinning, we'll see it just really struggles. It has trouble controlling itself or knowing what to do under these conditions. There, we'll see it almost got there, but it accelerated away from the goal. Just before it got there, probably an optimization it learned in the nominal conditions. And so the last thing I want to show is now let's consider again that same scenario, and we're going to consider this decreased motor gain and everything, but this time we train the agent in adversarial conditions where we allowed the environment to actually apply a force in any direction of its choosing to that agent. And when we actually train the environment to do this in the most disruptive way to the agent. If we do this, we can see that the agent is actually quite competent. Again, not quite as good as nominal, but it is again. And statistically, this is the trend we see over 1 million steps. And so one of the main takeaways here is that the way that the environment was adversarially perturbing, pushing on this agent is much different than the decreased motor gain, but it built the robustness anyway. And so that's really cool.
Hello everyone, I'm Raman Arora and I'm going to tell you about our recent work on multi-agent, multi-objective reinforcement learning as part of the IAA project. So many real-world applications involve interaction and cooperation between multiple autonomous agents. Nature is ripe with examples of such phenomena, and the goal here for us is to develop learning frameworks and algorithmic strategies to achieve similar goals for teams of learners. Consider, for instance, teams of autonomous robots playing soccer, or a swarm of robots combing through a natural disaster zone, or a fleet of drones in armed combat. What we would like to study is how multiple agents can collectively learn, collaborate, and interact with each other in an environment. Furthermore, each agent often has multiple competing objectives, for example, balancing exploration with safety, and these goals may be distinct for distinct members of the team. To study such multi-agent, multi-objective reinforcement learning problems, we are building Tanks World, a novel testbed that implements a team-on-team battle to create a dynamic multi-agent learning environment with an explicit trade-off between performance and safety. The goal in Tanks World for each team is to defeat the other team while causing as little unintended damage as possible. It presents a much lower barrier to entry for researchers interested in multi-agent, multi-objective RL. And solving Tanks World would require us to understand the dynamics of learning in settings that involve both cooperating and competing agents, as well as advancing state-of-the-art in RL to uncertain environments with large state action spaces. Leveraging recent advances in deep learning, for example. So far, we have considered environments that are non-stationary, but are not necessarily strategic. We are currently combining the two objectives simply as a weighted linear reward function, and using a standard off-the-shelf policy gradient-based method, the proximal policy optimization algorithm, or PPO. Each tank runs the same policy through the training and evaluation, and the experience of each tank is shared across the team by averaging gradients in the PPO algorithm. Okay, let's look at some evaluations. So in these simulations, the ally team is in red and the opponents are in blue. The green tanks are the neutral party. The numbers on the scoreboard indicate how many enemy tanks are destroyed, the collateral damage to the members of the learning team, and friendly damage to the neutral party. So what we have on the left is a randomly initialized policy, and there's no learning. No team really dominates the other, and what we see here is that there's no strategy, long-term or tactical. When we train the tanks to maximize the damage inflicted, it learns to be aggressive, but it is also indiscriminate. So the collateral damage and friendly damage both go up. The games, though, end largely in favor of the red team with a win ratio of at least 2-1. Finally, when we seek an explicit trade-off between performance and safety, we find the best policies that win more than 95% of battles and exhibit natural strategies such as teaming up and avoiding shooting at each other. All right, let me finish by saying that we are simply getting started. TanksWorld will allow us to answer fundamental questions about efficient collaboration in multi-agent oral, approaches for curriculum learning in strategic settings, and the role that communication plays in all of this. That is all we have time for. Here is a partial list of papers describing some of the work we presented. If you would like to chat more, please reach out to us. Our email addresses are listed here at the bottom of the page. And thank you for your attention.
Thank you, Ryan and Aurora. An excellent presentation. Coming next, I believe we're back to the physical domain adversarial machine learning for visual object recognition. Hopefully we've worked out the technical issues.
Hello and welcome to our presentation on physical domain adversarial machine learning for visual object recognition. So this project has three sort of lead PIs, myself, Alan Yor, then Yingxi Cao in CS, and Phil Belima at APL, and there's a set of other collaborators and students working with us on this project. So the project summary, the vision algorithms which you use for autonomous cars and for many other applications are known to be vulnerable to adversarial attacks, and this vulnerability will prevent assured autonomy. So the goal of our project is to design new attacks and defenses that are physically implementable and work in 3 dimensions. Realize a lot of attacks literature so far has been done on static images, and you really want to see whether these attacks can extend to the real world, where a car, for example, is driving around, and you still want to see whether you can attack the car, the autonomous car. Also develop toolboxes, tools that will allow efficient testing of these methods, both attacks and defenses. Design new attacks to videos, not just images, using dynamic patches, and then also develop new defenses which are resistant to these types of attacks. So now we'll start with my work, and then we'll proceed with some slides from Phil and then slides from Yingxi. So patch attacks using reinforcement learning can successfully make targeted black box attacks on deep networks on static images. So this is work we've done with support from this grant, ECCV 2020. So you can see it at the bottom. You have a car, you put in a patch here that's not very big, has a particular texture in it, and we have a policy that's learnt by reinforcement learning of what patches to select from our texture dictionary, where to put them in the images in order to attack the algorithm. And so these are over 95%, actually more like 98 or higher, and can make a deep network misinterpret an image as an object of your choice. That's to say it's a targeted attack. This is black box. You don't need to know anything about the interior of the algorithm that you're being attacked. Nevertheless, small patches like this can really mess up the performance of deep network algorithms, at least on static images. Now, what about defenses? Well, previous work of my group had developed a class of algorithms that we call compositional networks. These are a bit similar to deep networks. They have lower levels in common, but at the top levels, instead of being discriminative like deep networks, they have generative models of the spatial pattern of features that are going to occur for particular objects, conditioned on viewpoints. And on that, we add an outlier process which allows the algorithm to decide that some of the data can be ignored or rejected because it's not consistent with the rest. And for example, if you apply it to these images here, this is the attacked image, a CompNet can realize that these patches are inconsistent with the rest of the object, and so it can decide mostly to ignore them, but also to localize where they are. So over here on the left, CompNets and VGG16, both a very good deep network algorithm. Performance on clean images is about the same. If you do patch attacks, however, the CompNets are an order of magnitude more robust than VGGs to these attacks. VGGs about 99% success of attacks, and for this other method, an extension of it, the CompNets are, 2 orders of magnitude more robust. So 2D CompNets are robust to these, but since in the project we are particularly interested in images over time and in 3D, we are currently developing, extending the CompNets to being 3D CompNets, which are called NEMO. This means that the objects are represented by 3D meshes. Like the 2D CompNets, they're also rendering images. They've also got an outlier process, etc. So tests here show that these NEMO 3D CompNets are very effective at estimating the 3D pose of objects despite immense amounts of occlusion, far better than any deep network or any other method, and there's been 2 publications of that form. So I'll stop now, and now I'll transfer over to my collaborator. My collaborator.
Nancy or Phil, do you want to dub in live?
Yeah, so the essence of it is this, is that, much of the work that's been done for patch attacks really involves static imagery. And so what we've done is we've asked the question, what we want to do really is like to envisage the possibility of attacking a system, right? Like a navigation system, like an autopilot of sorts. And the issues of attacking a video are quite different. Then you're asking the question, how robust would be a static attack when the pose of the object that is being attacked, let's say, for example, the stop sign there, changes in time. By pose, we mean the position and the orientation. So as you imagine, like a car is approaching a stop sign, you're putting a patch, and you want the patch to be confusing to the eye in a way that now the stop sign is interpreted as being like, let's say, a speed limit, like a 60 miles an hour speed limit sign. So we have to consider different things here. Like one of them is, our patches that are static, somewhat invariant in their ability to attack. And the answer is no. What we discovered is that no matter how much you incorporate in your training vis-a-vis the knowledge of the pose itself, this 3D information of the orientation and position, then there are some failure points, of static patches. And so what you need to do, and Dave, I don't know if you can, but if you can push forward to the next slide, and I'll talk to it. But what we've tried to do is like we've tried to envisage the possibility that you can essentially use a dynamic patch. Okay, so the idea of the dynamic patch, and now you can let it run if you want, and you see like the sort of like dynamic patches there that are being created. So what you see there is that for different type of targets, so that is, like we translate the interpretation of the eye from being looking at the stop sign to like something else, like a mop, gas mask or football or whatever. We create these like dynamic movies that correspond to, the relative, adapting to the relative pose of the object being attacked and the observer. And we show, and it's not like a great insight, but you can show that you can really be much more threatening and much more effective in terms of attacking this way. And so the takeaway is that, hey, we should really think about those issues right now, because now the problem is elevated, and we may have a situation where we have dynamic attacker or smarter attacker than just people who put like stickers into stop signs or whatnot. And the last thing I wanted to show is that at APL, we've developed different type of frameworks. Some of them are in vivo, some of them are in silico, quote unquote. So at the top here, like this in vivo framework allows us to do like evaluation of effectiveness of patch attacks using Teslas. On the bottom, you see, like, for example, we are doing like electronic insertion. Maybe if you can stop just one moment. Electronic insertion of patches, and then we can evaluate very effectively if patches that have been optimized are attacking under different type of situation. And last, what I wanted to say, just to introduce what Yingzi is going to talk about is that, there was an interesting intervention at a workshop that, all of us here like helped organize at ICCV this week by Carlini, which is one of the main researchers in the community at Google on AML. And he said, we have to pivot from looking only at attacking computer vision or NLP or whatever to like attacking like full stack systems that are doing like autopilot, for example. And that's what Yingzi and his student have started to do in the next and explain in the next couple of minutes. And I apologize for like all of these video issues. So anyway, I think like the sound is not there, but so essentially what Yingzi has been doing is that he's imagined the possibility, and he's done that using rendering engine at this point in time. And so the idea is like to eventually bring that into like the real demonstrator. But he said these following things, like what you're seeing there on the left is a truck that has a dynamic patch, printed on a truck that's trying to remotely control the autopilot of the car that's following it. So the idea is that, can you change the patterns by misleading the vehicle that's following it as to, the road itself, and then make it change its heading. And so you can do the same thing, by trying to make it accelerate or brake or whatever. So the idea is that the car that's following the truck, the truck that's presenting this dynamic patch there as being shown, the car becomes like a slave, and is induced to like doing steering. And you can imagine all sorts of possibilities. So again, what's interesting about this problem is that it lies at the intersection of computer vision and as well as all the security issues. So what you have to envisage, what are the incentive and what are the different settings in terms of like the possible attack that exist there, and what is the realm of the possible, so that you can now turn around and develop defenses against those possible threats. And more examples here of like making this dynamic patch attack that are attached to the truck in this simulation environment. And so again, the idea is that once we have this going and the patch is optimized and etc., can we take that in real life and see if we can also implement that using the APL, Tesla demonstrators. As you can see there, like the car is induced to cross the median based on the autopilot deciding to cross the median based on what it's seeing from the dynamic patch.
Thank you very much. That was excellent, especially under the circumstances of the audio issues. The next presentation will be values, which are verified assured learning for unmanned embedded systems. That will be presented by Aurora Schmidt and Marin Camilleri and Greg Hager.
Give a brief overview of our project, Verified Assured Learning for Unmanned Embedded Systems, or values. The main objective of the project is to enable reliable operation of autonomous systems in complex environments, motivated by applications in autonomous vehicles as well as robotic surgery. And really, the objective is to be able to assure performance and safety of systems that consist of both human-coded algorithms and software components, but also machine-learned algorithms and components. The team consists of a number of folks from both APL and Johns Hopkins. The main components of our architecture that map to research trusts are as follows. First, we have a set of physics, known physics and logic-based components that are integrated with a set of learning-based components so that they can produce a combined policy which can then be formally verified by safe by construction fallback layer, which, in extreme unsafe situations can override the original controls of the system. And the main applications that we were looking at were to unmanned ground vehicles that operate on natural terrains, as well as in robotic surgery. And today we'll just mention a few highlights of the project, most related to the ground vehicle application area. So our main objective here is to focus on uncertainty-aware decision making, and particular use case was the navigation in unstructured or rough terrain environments. We have built a small 1/5 scale unmanned ground vehicle with the idea that we would like to task the vehicle to be able to very quickly navigate between any 2 points on campus, and really then it becomes a way to trade off between speed. We'd like the vehicle to move as quickly as possible, but also safety. And two of the interesting questions that come up in this setting is how can we safely deal with pedestrians around us? And the second is how can we safely traverse not just paved surfaces, but also unpaved or rough terrains to gain efficiency. So why is this hard? Well, on one hand, actually predicting how agents will move in the future remains a challenging problem. In particular, here if we look at the upper right, we can do a pretty good job in perceiving the current state of pedestrians, their current position. And in fact, we've developed a system that uses a deep neural network together with depth sensing as well as bipartite matching data association to be able to both perceive and track pedestrians over time. What still remains challenging is actually figuring out how are they going to move in the future so that we can safely navigate around them. On the traversability side, we can fairly easily figure out how to separate the paved surfaces from others, using, for instance, semantic segmentation as well as geometry. But we want our vehicle to be able to navigate on other surfaces as well, for instance, grass, slopes, gravel, and so on. In this more general traversability, problem remains very challenging. A few months ago, over the winter, we developed an integrated set of algorithms, perception, control, and planning on the vehicle, so it can execute basic missions. Again, limited to those paved surfaces. It can avoid pedestrians and do a reasonably good job in somewhat benign environments like this. And one of the key simplifications here is that we did not fully account of the uncertainty of those agents around us, and we wanted to kind of be able to fully account for that, because that's the only way to really guarantee safe navigation of the vehicle. And so one way to do that is to actually explicitly account for how the motion of other agents evolves during planning. And so what we did in this algorithm is to introduce the notion of an intent or a goal for pedestrians. In other words, we can estimate where would they want to go, and what a motion in that direction would look like, and then how do we make sure that we avoid that motion. And this is represented in a probabilistic way. Particularly in this video, this can be captured by basically this little red square, which marks the most likely intent or goal for the pedestrian, and then the green ellipsoid is the kind of high confidence region where we have detected the agent. The algorithm that we developed is called actor-critic probably approximately correct policy search, which essentially minimizes a statistical upper bound on both performance and safety, where safety is probability of collision. And here these graphs show how these two metrics evolve in time. We can skip the details of this algorithm and just quickly mention also that another important part of the project that we recently developed is the ability to incorporate these uncertain representation of other agents represented by covariance ellipsoids, and also incorporate that in our safety fallback logic, which here we can see kicking in with this pedestrian who is kind of aggressively heading towards the vehicle, where here we switch from our normal driving to the safe policy kicking in, so that the vehicle temporarily hit the brakes, and then afterwards it continues navigating. And then here we can again see the uncertainty of the other agents around us being represented. So this system is definitely not perfect, although it is some initial steps towards properly accounting for that. Here's another example that shows that we can kind of give more room when we go around pedestrians, but we also do some weird things from time to time, like here we stop for no reason, then we continue. Actually, it turns out that we still have some problems when agents are coming in and out of the field of view of the vehicle. That's what was happening here. So in the interest of time, I think I'll hand it off to Aurora.
In task 2, we want to build a provably safe fallback controller to perform real-time runtime monitoring and assurance on the ground vehicle. And the way we are going about this is we are using formally verified collision avoidance theorems developed in the air domain and trying to apply them to driverless vehicle scenarios. On the left plot with the planes, you can see that we map out the potential trajectories that the planes can take over time and exclude the possibility of collision using climb and descend maneuvers. We map this to the vehicle domain by modeling the down the road distance versus the cross lane distance rather than altitude versus time. And again, we want to make sure that those two distances do not coincide at the same time. And so we're able to apply the same verified safety theorems, but in a vehicle domain. This previous approach to synthesizing a provably correct fallback controller is actually published in some former work by Kuskalas et al. And this is the method that we're going about trying to synthesize a safe emergency stop system for the Values Project. Here are some examples of applying these theories to safe fallback control. The first example shows an anticipatory emergency braking scenario where the red car is cutting in front of the green car. When the green car detects an impending incursion on its horizontal location, it has to reduce its speed to make sure it doesn't collide with the vehicle that is now in front of it. You can see it turn yellow when it engages that safe velocity control action. The second example shows the same kinds of approaches applied to a merging scenario. We are preparing these collected approaches for safe fallback control into a system called safe defensive driving, and we have integrated this safe emergency braking approach for pedestrians into the ground vehicle testbed and are demonstrating the fallback controller quickly responding to pedestrians that are detected and braking for them when safe navigation cannot be ensured.
Okay, up next will be regression analysis for autonomy performance comparison. This is Paul Stankwitz and Marin Kavalarov.
Hi, this is Paul Stankwitz with the Johns Hopkins Applied Physics Lab, and I'll be giving an overview of our work in identifying performance regression conditions for testing and evaluation of autonomous systems. And so with regards to background, this research falls into the category of improved test and evaluation methods for autonomous systems. Specifically, how can we make better use of large-scale simulation-based testing for autonomy? And this is necessary because, as everyone knows, trying to predict how these complex systems will perform under all possible conditions is extremely difficult, even for the developers who are actually writing the code. And so to lay the groundwork, those three sub-bullets kind of list the increments of how autonomy software has and is currently tested. So these would consist of things like basic unit-based software testing, handcrafted simulation analysis, and then a step further being Monte Carlo style simulation-based testing. Ultimately, if you define the testing parameters you want to vary and some performance criteria to score the output of the simulation, what might come out is a scored simulation data set, something like what this 2D example plot looks like for an obstacle avoidance scenario. So each of those dots is a simulation that was run, and the resulting performance of the system is the color. Now with this research, what we're looking to address is the technology gap that exists in not just identifying failure modes within a single study, but have identified changes in performance between two of these data sets. So this is the idea. Imagine you're a robotics developer and you go to evaluate your system with this type of simulation-based testing. Let's call this version A on the left. And based on this testing, you identify problems in that red box on the left plot and go back to make software changes to improve performance. We'll call this version B on the right. Naturally, you want to test this new version, and with these complex interacting systems, traditionally you may have needed to just cross your fingers and hope that your software changes both fixed the original problems, but then also didn't introduce new types of failures. So the red highlighted region in these images would be an example where you improved a failure mode in version B, whereas the gray highlighted region would be an example where version B has a new failure mode that didn't exist before. Essentially an unintended consequence introduced by the software changes. And so this technology gap is what is driving our research statement, where we would like to utilize statistical learning to automatically identify changes in autonomy performance between testing data sets from different software versions. And in this way, we gain valuable insight into where these new failure modes may be popping up unexpectedly. So now getting into how we're approaching this problem, this slide gives an overview of the algorithmic approach to do this regression analysis, with the main pieces outlined in this diagram using 2D example plots to illustrate. So on the left, we start with two non-identical performance data sets like what was discussed as part of the background. In this case, for example, coming from two Monte Carlo simulations. And when I say non-identical, I mean that the scenarios are different for each set. Then, as I mentioned, we apply statistical learning techniques to fit surrogate models to the data and then ultimately extract out clusters of scenarios that represent high probability regions of suspected performance regression, ranked by those that are most severe. And one of the nice features you'll notice is that this paradigm has no notion of a specific application of the data sets, as long as the data is normalized and follows a black box input-output relationship. Thus, this framework could be used on any application that produces these types of testing data sets, such as self-driving cars, testing parameters related to aircraft, or even testing data sets related to maybe some image classification problems. So then diving a little deeper, in the first step, the regression modeling box, what we've proposed to do is smooth the data by fitting surrogate models to each data set and then predicting each set on the opposite surrogate model. And through some experimentation, what we found were that quantile random forest models were best suited to this task, particularly since these testing data sets are typically large, high-dimensional, and highly nonlinear, as you saw even in that 2D background example. And they're also able to provide prediction bounds on the estimates, which then lets us use the upper bounds of these estimates to focus on high probability performance regression. And what the regression modeling step ultimately gives you is a regression data set that is now comprised of the predicted changes in scores. And so once we have these predictions, we can then do several things to pull out relevant features of the data using unsupervised learning in the second step, the regression clustering step. And the idea here is to first separate the data in the output space using Gaussian mixture models to naturally group areas of severe failure versus moderate failure. And then subsequently, we take those clusters of different scoring changes and recluster in the input space using density-based methods to separate failures that occur due to different combinations of testing parameters. So each one of those different colored regression clusters in the bottom right is its own pocket where performance has degraded due to different conditions, where ultimately we want to display metrics about these clusters that give the analyst insight into the causes for the decrease in performance. All right, so that gives a high-level overview of the approach, and to test its efficacy, we first started by testing the regression modeling aspects on test functions loosely designed to mimic the nonlinear nature of autonomy performance. From there, we did a Monte Carlo analysis where these testing functions were randomly generated between 2 dimensions and 10 dimensions, and we produced testing data sets ranging between 500 samples to 25,000 samples. Overall, when comparing the quantile random forest modeling to both multi-layer neural networks and Gaussian process regression, what we saw was that QRF models offer the best combination of low prediction mean absolute error over the different functions, while also being able and the best at minimizing prediction outliers, meaning it's very rare for the upper QRF bounds to miss true performance regression. And so while this paradigm could be applied to any array of problems, we also performed a case study of what this analysis looks like applied to an autonomous surface vessel navigation problem. For this application, the data sets you'll see are for a 3D input space where the ASV navigation was tested against parameter variations for an oncoming target ship that it had to avoid. So variations of the heading and speed for the oncoming target vessel and a measure for displaced closest point of approach. The performance of the ASV in each simulation was then measured with respect to certain mission safety and navigation criteria. So given these conditions, here you see a similar analysis with these data sets as what we saw in the example diagram, only now we're looking at 3D testing sets for 2 different versions of ASV software. For this example, version A serves as the baseline, while version B was meant to improve ASV performance in overtaking scenarios, essentially the region highlighted by that red box on the left. On the right then, you see what would be the output of the regression modeling step in the form of a regression data set that predicts the change in performance between the versions. Qualitatively, we can see that we did in fact improve performance in that desired region, but there are also some areas that appear to now be performing worse. And so finally, in the regression clustering step, after this is applied, it extracts out the top 3 regression clusters from this data as those that represent the most severe decreases in performance. The top regression cluster is shown in blue, and we've extracted out 2 scenarios from versions A and B within this cluster to show the new unintended behavior of the ASV system. In a nutshell, the software changes applied to version B, while improving performance in those overtaking scenarios, now cause the ASV to turn to starboard in shallow crossing scenarios, even when this results in a near collision between the 2 vessels. So it's this type of analysis about why this region is regressing that is extremely useful to developers in knowing the problem areas of your system. And so for next steps, the vision for this tool is as part of a larger augmented continuous integration framework for testing autonomy software. We're hoping to extend the traditional CI pipeline by continually evaluating more of the holistic decision-making performance of the autonomy software. So that bottom right area being highlighted is where this research fits in for comparing previous performance against current performance. The idea is that this type of a loop could be run continuously to provide automated reports to developers that give information about shifts in performance and unexpected failures. That way you have a much more informed picture about the development status of your system and aren't blindly playing whack-a-mole with different failure modes. So with that, I'd like to thank you for your time, and if you'd like more details on this subject, feel free to request our IROS paper cited at the bottom there.
Thank you, Paul. That was an excellent presentation. Our final presentation will be identifying factors to explain the behavior of deep learning systems. This is Mark Dredsty and Anna Buchak. Presentation will be up shortly. And remember, afterwards is the breakout session, and the URL is available on the chat.
Hi, my name is Mark Dredsty. I'm a professor of computer science in the Whiting School of Engineering, and my co-PI on this project is Anna Buchak, who is at APL and AMDS. And I'd like to talk to you about our IAA-funded seed project, identifying factors to explain the behavior of deep learning systems. So our goal here is to enable AI systems to explain their decisions. AI is really powerful in what it can do, we all know that, but there's reluctance in many domains to use AI because deep learning systems, which are really driving AI forward at this point, can be very opaque. And decision makers are often relying on AI systems to make their decisions, or even considering deploying AI systems autonomously, but they don't want to do that unless they have confidence in the decisions. And one of the ways that we can help them build confidence is by helping people understand how systems make decisions. And that is really the goal of this project. So our focus in this project is on interpretation of complex systems behaviors that are fundamentally not making decisions as humans make decisions. And that's really a significant gap between the way AI systems operate and the way people do. AI systems might be effective, but it doesn't mean they're thinking like people do. And we want to help bridge that gap to explain those systems' behaviors in a way that people can actually understand what they're doing. We don't want to replace these systems. So one of the criteria that we have for this project is to use existing AI systems, which already perform well. We don't want to ditch those systems in favor of systems that might perform not as well, but more explainable. What we want to do is bring explainable technologies to those systems. So the way we're going to approach this is that we're going to leave these AI systems in place, and we're going to treat them as black boxes and try and explain the behavior of what's going on in ways that people can understand. So the primary application we're going to work on is disruptive event prediction. So this was a project originally developed on a propulsion grant called that funded project called Crystal Cube. In that domain, our goal was to try and predict before it happened, to forecast major disruptive events. So this would be things like leadership changes like coups, uprisings. This would be riots, typically violent riots. These sorts of things that we'd like to identify when they're going to happen before they actually happen. The justification here is that if we were able to do this in advance, we can do a lot to try and align certainly aid and policies in order to ensure the best outcomes. So for example, the US government, if it knew where there was going to be a disruptive event, where there was likely to be significant disruption, we could do our best to try and provide aid to people, or at least to align US policy and US resources in advance, instead of scrambling when these things happen. So I don't want to get into too much detail on how Crystal Cube works, but the base system here is a recurrent neural network. It uses a lot of different features from a lot of different systems. It uses these features in complex ways, such as like training autoencoders, and it uses that to make predictions. So this was a system that works very well, took a lot of time to develop. We don't want to change this system. We want to leave the system in place, but we want to help policymakers understand what the system is saying and why it's saying it. So there are going to potentially be major decisions made based on the predictions of the system. We need to explain the system's behavior. So we have two tasks or two projects within here that we're working on. One is inferring rules from model perturbations. The idea here is to take inputs to these systems, try and perturb the model and perturb the inputs in different ways, and look at the output of the system and try and generate rules that people can understand. So even though these rules don't match quite how the system behaves, because it's not a rule-based system, we can use these rules to approximate the system behavior, and rules are much more understandable to people than the way neural networks normally process information. So we want to be able to generate rules like if there are violent protests, and there are many of them, and if the repression is medium, then we expect that a regular leadership change is very probable to occur. And that's something that is very intuitive to a person, and they can say, oh, if that's why the system is predicting or forecasting this event, then I'm going to have more faith in that happening. The other project we're working on is proxy models. And the idea here is to trade off between faithful predictions. So these are explanations. These are explanations that are faithful to how the model actually makes decisions, along with trading off faithfulness with plausibility, which are, do these models make sense to a person? And the way we've chosen to do this is by using a proxy model. So here we're going to leave the complex network intact. Instead, what we're going to do is train a much more friendly, simple network that runs parallel to the main system. And the goal of this simple method is not to do well at the task, but to mimic the behavior of this complex system. So it's obviously not going to be able to capture the behavior. These neural networks are very complicated. The proxy model is just an approximation, but it's a very interpretable model. So therefore, it's going to be very understandable to humans to figure out what's going on. So we're using this to explain Crystal Cube predictions. And so what we do here is we take the Crystal Cube system, we train a simple model. I think we're using linear regression. We train a linear regression model looking at the inputs to the Crystal Cube system on one end, and then looking at the outputs, the predictions of the system, not the correct answers, but what the system's doing. And we train a linear regression model to mimic that. So it doesn't come it's not perfect in mimicking it, but it's pretty close actually. So it doesn't do as well at the task as the Crystal Cube system would, but it does give us a way of modeling the Crystal Cube system. And so now what we can do is we can look at that proxy model, and we can look, in this case, since it's linear regression, we can look at the coefficients of different features. And across our whole data set, across all the predictions, we can say, here are the features that are really important to the way Crystal Cube makes decisions, and here are features that are not very important. And then for specific examples, we can see which one of those features were triggered. So we can offer explanations that are globally consistent across the model, as well as pick out from those global explanations which one apply to specific examples. This is a very general purpose method, so we're also using it on medical data, so a very different domain. Here we are using the well-known MIMIC ICU dataset, and we have ICD, I think it's 9 coding, or I think we're using 9, not 10. And we have here a different model, but we again have a series of fairly complex deep learning models. We have a CNN, convolutional neural network. Camel is a model specifically developed for this task, which is a mixture of a CNN and some other things. And we can train a logistic regression model to mimic the behavior of these models, and then ask it to produce explanations, which is basically saying, please look at this text that has this label that you've predicted. Which pieces of the text are most closely related to the output? And we can actually get really similar behavioral decisions. Really similar explanations that are really plausible to people. These are annotations from doctors, so we know that they make sense to people. And we can also measure, hey, this proxy model is actually doing a really good job at mimicking the complex neural network model. So we can, again, trade off plausibility and feasibility. One of the some of the benefits of our model, and the reason we want to look at these other domains, is it is primarily two big improvements over existing methods. So we have another paper comparing our proxy model to a wide range of other explainable AI-based methods. So one is our model is really fast. So LIME, which is a really popular method, took about 140 hours on our Crystal Cube data set to run. The gradient-based methods we tried take about almost 2 days. The proxy model is just training a single logistic regression model and then using it for every example, right? So it actually just takes a couple minutes to train. So it's incredibly fast by comparison, and there's no cost once you've trained the model for looking at new examples, whereas LIME incurs a cost for every new example. We also can better trade off this global-local distinction. So issues like LIME and gradient-based methods are often local, where they look at a single example and they say, okay, how do we explain the predictions in this example? But the problem is the explanation for this example might look very different from another example when they shouldn't be. People don't make decisions differently depending on what they're looking at. They have a certain rule set or a certain way they make decisions, and they apply that somewhat consistently across many examples. And so that's how our method works, is it actually it's trained on the entire data set, so it's global in nature, and then we can say, okay, for this whole data set, what are the most important pieces of information that drive decision behavior, but then which ones are active for each individual example it sees. So that's a brief summary of the work we've done so far. We're really interested in other application areas for which we can apply our methods, especially in the medical domain. So if you have examples that you think would work well for us, either, for example, you have a system and you want to generate explanations for it, especially systems that are around language data we're particularly interested in, our team would really like to hear from you. Thanks. Happy to answer questions.
Okay, let's thank you very much, Mark. Let's all jump to the breakout rooms. It'll be extended a little bit. I know people are there already, so please follow the link to go to the breakout rooms. Thank you. Bye. See you there.
If you have any questions about how to get over, feel free to message me. I'll hang out here for a minute. I've put the Zoom information in the chat. The shortened Zoom link will take you directly there as well. That's that bit.ly link that I wrote out. It is bit.ly/KSE_breakout. Let me know if you have any issues. And we'll be over there until 12:35. At 12:35, don't forget to come back here for the afternoon session. Hello, everyone. We are closing out the Zoom rooms that everyone is currently in. So it'll be just another minute as we rebuild our audience. Deborah Matthews will be kicking us off in just about, I would say, 3 minutes. We can go ahead and get started, Deborah, around 12:40, if that works for you.
Will do.
Thanks.
Super. Deborah, I assume that is, you've got control of the screen there now?
It appears so. And
All
I
right.
assume that means you can see my slides.
You can see your slides. And I'm looking for our Master of Ceremonies and coordinators here, David and Veronica. You give us the thumbs up when you want Deborah to go. It looks like we've got 50 of our people back with us again.
I think we're good to go. It's 12:40. So,
All right, well then I will go ahead and get started. Welcome back from the breakout rooms. My name is Deborah Matthews. I'm the ethics and governance lead in the Institute for Assured Autonomy and also a faculty member in the Berman Institute of Bioethics, where I'm the assistant director for science programs and core faculty. So I also sort of serve as a bridge between the work that the IAA does and the work that the Berman Institute does. So, there we go. So within the IAA, ethics and governance, I would argue, and I think most of us would argue, is intimately related to questions of assurance and what it means to have an assured autonomy. Within the IAA, ethics and governance is both sort of structural as one of the pillars, and with my role within the Institute, and sort of infused throughout. We have already completed and have some ongoing research, and I'll talk a little bit about those in a minute. And you've heard about some of it already today. And we're also working to create more activities and opportunities to do additional work on ethics and governance within and across the Institute. That includes an upcoming roundtable on assurance, which I'll say a little bit more about at the end, in which Jim alluded to right at the beginning of today's event. So with regard to completed and ongoing research within the IAA, I mean, you learned about some of the ethics and policy issues being addressed in the seed projects already. You know, for example, the Assured AV policy. And the IAA has also funded internal work listed here. So work on AI safety and assurance by Aria Englander and Yijing Wang that was sort of provided a summary of the current state of AI safety and assurance research to help us sort of identify and situate ourselves in the field and identify gaps where we might be able to provide new information and research. Second project on trust by Josh Baker and Ariel Greenberg. It is sort of a complementary piece of work that does deep dives into a subset of issues in AI ethics, including existing guidelines, their trust and trustworthiness, and notions of autonomy. And then finally, there's this work on human-centered trust and the Assured Autonomy Roadmap by Sarah Rigsby, Alexis Basantis, and Matthew Gumnich. And you're going to hear more about that in the lightning talk. So I'm gonna leave that to them to talk about. But ethics and governance is also much broader than that. You can ask questions about, how is ethics explicitly coded into systems? How is ethics unintentionally baked in to systems? And you've heard a little bit about some of these earlier in the day. The ethics of use, and then questions of governance. And governance here is a word that it's broader than policy or regulation or law. It's meant to capture a broad range of activities that are designed to facilitate, constrain, or otherwise shape the use and trajectory of technology. So in the next few slides, I'm going to say a little bit more about each of these and give you some examples, because I want to give you an idea. I know that not everyone in this space thinks about ethics all the time like I do. And I want to give you sort of a sense of the kinds of questions that are being asked in this space. So with regard to explicitly coding ethics into systems, these are questions about primarily embodied systems like robots, like the systems that we saw earlier in the day walking around in social, or not walking, moving around in social environments. Like, what needs to happen for a robot to know that a particular action could harm a human and to decide not to do it for that reason, rather than you have coded it to not do that action, right? So in order for a system to do that, it needs to be able to identify an agent in the environment that can be harmed, to understand what can harm that agent, and to understand how that harm can be inflicted, and then decide not to do it. That's a lot of steps that need to happen in order to enable a system to make a truly ethical decision about its behavior. And how do you get, a system to reason about not just issues of harm, which are relatively, like, that's the easiest possible case, right? Like, don't hurt someone. But beyond physical harm, other kinds of harm can be really culturally specific, and beyond harm into other kinds of ethical issues is even more difficult. Ethics, even when ethics is not sort of intentionally coded into systems, it nonetheless gets sort of smuggled in by the people who are building the systems. And I think it's sort of worth noting that that's not generally a particularly diverse group of folks, right? I mean, I think that probably the most common issue we think about here, or that's discussed here, is biased training sets. Right? We know that humans are racist and sexist, for example, and those biases are clear in our medical, social media, and other data sets. And when those data sets are used to train systems, the systems very quickly learn those biases. There's also issues related to labeling, right? By which I mean a mismatch between what the algorithm is supposed to be predicting and the proxy variable that was selected and which the algorithm is actually predicting. So for example, you might have a healthcare algorithm that is designed to assess future healthcare costs and direct additional care and resources towards an individual, but, future healthcare needs. But the variable that is chosen to try to assess that is future healthcare costs. But because of what we know about structural inequity in our system, we know that not everybody has access to care and therefore accumulates costs in the same way. There's a similar mismatch between trying to assess creditworthiness, but using income, or assess criminality, but using arrests and convictions, given what we know about the biases baked into what someone's income is or whether or not they've ever been arrested, right? In this country, brown folks get arrested way more often than white folks. And that doesn't necessarily match with notions of criminality. And what this can do then is exacerbate existing inequities, right? Which is not what we want AI to do. You could also have narrow or inadequate functionality. For an example, the Apple Health Suite was originally not designed to include menstrual period tracking, which 50% of the population might want and need. And then all of this leads to questions of fairness and other kinds of fairness, justice, and other kinds of broader ethical issues. With regard to ethics of use, here we're talking about, for example, what kinds of testing should be required before systems are deployed for safety and efficacy, et cetera. What should patients or physicians be told about the systems that are being used in their care? Should consent be required? Or people applying for home loans, what should they know? Should consent be required to the use of these kinds of algorithms? And what are the privacy protections? And again, you heard already a bit about privacy in one of the prior presentations. And then with regard to governance, this is still very much developing AI governance. And there have been many, many statements and guidelines developed globally about the ethical principles that should guide AI, and the most common set of those is listed here. However, different documents and institutions and people are using and understanding these terms in very, very different ways. And very little work has been done to figure out how to concretely translate these ethical principles into governance approaches at all stages of technology development and deployment. And that's part of what this roundtable that I mentioned earlier in the presentation is designed to address. And one of the ways that the IAA is trying to sort of fill in some of these holes. Other governance level questions are, what are appropriate roles for robots at all? Where should they be active, caring for whom or doing what jobs, et cetera? What kind of decisions and ethical decisions should autonomous systems be permitted to make? And importantly, who gets to decide and by what means? So there are lots of I've tried to give you sort of a broad sweep of the kinds of ethical issues, different categories of ethical issues that are being addressed both within the IAA and across the field. And I would love to hear, I think we might have a couple minutes for Q&A, but if not, I will be hosting a breakout group at 2 o'clock. And my email address is also on the last slide. You should feel very free to reach out to me with questions. But I would love to hear about, either in the Q&A now or in the breakout group, about the kinds of issues that you don't think are being addressed, that you recognized in your work, but don't think are being addressed. Are there issues that are being raised by your work that you want to think about or study? And are there ethics or governance issues that you want to work on, but you need a philosopher or a social scientist or an ethics type person to help you think through the issues and collaborate with. So again, happy to take questions now if we have time. Alternatively, I'll be hosting a breakout group at 2, and my email address is there at the top of the slide.
Thank you, Deborah. We've got about 2-3 minutes for questions. So if anybody has any questions, feel free to throw them in the Q&A section. Otherwise, I'm sure we're all excited to talk to you during the 2 p.m. live session. All right, Deborah, it looks like you got one question in the chat from George. It says, can you describe more about the work in human-centered trust?
I am going to leave that to Matt, who I think is giving the very first lightning talk right after this. And it's his work along with Sarah Rigsby and Alexis Basantis.
Let me give my lightning talk, and then if there are questions, we can address them in the breakout session afterwards. I think that's probably our best bet.
That sounds great. I guess since that's the question that we've gotten, if it's okay with Deborah, we can pass it on, and Matthew, you can give your presentation now.
Yep, absolutely.
Sure.
All right, we'll get the slide deck back up, and then Matthew, you can kick us off for the first 3 minutes. Next slide, please.
Yep. Okay. So when we consider assurance of autonomous systems, we need to think about what a world of assured autonomy might look like, not just from a technological perspective, how is our technology assured, but from a human-centered perspective as well. To really explore that and to dive into this challenge, the human-centered design team for the IAA went through a series of interviews and did research, and we learned a lot of really interesting things. The first thing we learned is that assurance really requires a relationship at its center between people. Assurance rises as a result of healthy relationships between two sides. The stewards or builders of the technology on one side, and on the other side, the recipients or users of the technology. The recipients ultimately are putting their trust into the stewards, trusting that they will be kept safe and that they will not be harmed. This means that these stewards then have a responsibility back to the users, that the autonomous technology should do no harm and that the patronage of the users won't be exploited. But as we know, all these relationships take work, and that made us want to learn a lot more about what trust actually is. So how do different domains talk about trust? What does it mean to trust technology? And how do you create technology that is worthy of being trusted? We learned that trust is really a very tricky concept. People are driven by their experiences, especially if those experiences are extreme. Humans may trust technology until proven wrong, or if they have a really negative experience, it could affect their willingness to trust any technology in general. And that negative experience could be associated with a person or a company or a kind of technology. Furthermore, humans are social, and we can have membership in many different kinds of communities, and those communities can overlap and interweave in different ways. And each one of those communities will have different views on what constitutes beneficial technology or what it means for a steward to provide them with a trustworthy experience of some sort. So while it's really important to understand what the capabilities of the technology are, it's a lot more than that. We also need to think about the humans on the other side of this relationship. The institutions and organizations that influence and control technology and their credibility, for example. They are the ones that are bringing us these technologies and helping integrate them into our lives. So understanding the motivations and credibility of those institutions and organizations ultimately is what is going to build trust and enable the adoption of that trustworthy technology. And so when taking a holistic look at all of these components to assurance, this really is the human-centered trust framework, the relationship between these users and the builders and providers. And that's all I've got.
Thank you, Matthew. Sorry, I was stuck on mute. All right. Up next, we have William Walton with his presentation.
Hello, my name is William Walton, and I'm going to talk about upstream data fusion of digital breast tomosynthesis and ultrasound imagery. What I'm going to show is that by processing multiple views, we can improve the classification of lesions in breast cancer. And this is our relation to assured autonomy, processing multiple views and the improvements we get. In my diagram on the left side, what you see are the three inputs to the system that I'm showing. The upper left image is a X-ray image taken from the craniocaudal view, or the top-down view of a patient. The next image in the middle is a medial-lateral oblique view taken from an angle. These are two common views that radiologists use when examining patients. And the bottom image is an ultrasound image, another modality that is also used for breast cancer detection. What the system does, going from left to right, we first process each view individually. We compute features. Those features can come from engineered features, image processing features, or from deep learning. The outputs of those features, or each feature, is fed into a classifier, which again can be a convolutional neural network or something as simple as a support vector machine. But what's important is the output of each classifier is actually a likelihood value, a likelihood of benignness or malignancy, along with the location of candidate detects that were found across the breast tissue. From each of those individual inputs, they go into a data association process. And that process, in plain English, really tries to match different detects from each view that correspond to the same object in the breast tissue. Registration capabilities can help in this process of matching. The output of the data association goes into a Bayesian classifier, because what we really want is a probability of malignancy for the various hypothetical objects that are found. So on the right side are the different outputs to the system, but perhaps what is most important is the lower right, the classification accuracies that you see. What you see is that from each individual modality, CC, MLO, and US, you see the probabilities of malignancy, the classification accuracies that we achieve. But what's important is at the bottom, what you see is the classification accuracy significantly increases when we process them jointly. From probably about 60–70% accuracy up to 91% accuracy. And so that shows the power of fusion and the strength from jointly processing the different image modalities, harnessing their strengths and differences. For more information about this, you can feel free to check out our publication. Just do a search for Porter UDF mammography, IWBI 2020. And our email addresses are also shown just to the left of the table. If anyone is interested in collaborating, feel free to reach out to us. Thank you very much.
Thank you, William. Up next, we have Mei Lau presenting.
Good afternoon, everyone. I'm here to present a project we started last year called SAGE, which stands for System Automation Guidance Evaluator. And to kickstart this, traditional risk assessment really focuses mostly on safety, failures, reliabilities, but the impacts of these newer complex technology developments involving AI and automation extends beyond that. And in other words, there is no existing standardized application capable of evaluating the multi-domain and long-term impacts and risk associated with level of automation and task allocations between human and machine. And the objective of our project is really to seek to employ a human-centered approach to develop a framework and a suite of associated interactive decision aids for AI and ML technology risk evaluations and task allocations to empower people to make the optimally use automation while preventing like a disastrous end. And we seek to assure that autonomy by identifying the risk and mitigation techniques that is associated with like broader domains, including but not limited to like political, social, ethics, environment, and looking at longer term impacts from like 5 to 10 years, giving them advice on, hey, you know, based on all this information, this is the level of automation and task allocation we would recommend, and here is the risk associated if you don't go this route, and how to mitigate it. This project is really at its stage of infancy. We fleshed out some of the concept from the AMDS Innovative Initiative, doing some literature reviews and having SME interviews, as well as like developing a prototype in use case to demonstrate representative inputs and outputs of how the system can work. And shown below here is a notional prototype consisting of the input from system designers that can with specific questionnaires to break down system features in terms of task, human, system, and impacts to gather all those necessary data for the machine to the application to do its job, magic job, behind the scene with analysis and providing outputs as mentioned before. Include like the recommendation of automation allocations, task allocations, what are the risk impacts in the different multi-domains, how do you mitigate them, long-term risk projections, and like trade-off matrix to give people the knowledge they need to make informed decisions regarding automation usage. And that's it in a nutshell. Feel free to contact us if there's any collaboration or opportunities you foresee. Thank you.
Thank you. All right. Up next is Richard Day.
Good afternoon. Thanks for the opportunity to share this work. My career has been all about mission success and mission assurance, whether at NASA, at APL, or now with Whiting and JHM. Mission assurance principles apply broadly to many domains. To NASA space missions, the critical and complex challenges addressed by APL, and even healthcare, and the mission of Johns Hopkins Medicine. At the Armstrong Institute, our mission is to eliminate preventable harm to patients and to achieve the best patient outcomes at the lowest possible cost, and then to share knowledge on how to achieve this goal with the world. So regardless of the domain, how do we assure mission success? It boils down to rigorous risk identification and assessment, timely informed risk decision-making, and effective mitigation actions. With the power of Hopkins in-health precision medicine, we aim to transform healthcare safety and quality. The ability to synthesize operational insights from extensive heterogeneous data will allow us to identify, analyze, and evaluate previously invisible risks and opportunities. AI will dramatically improve our risk-informed decision-making with a combination of autonomous risk assessment and leadership mitigation actions. We prioritize our projects with immediate opportunity for real-world operational impact while building toward a comprehensive mission assurance platform. Our first project is a top 10 national safety priority: prevention of wrong site procedures. The project uses a full range of discrete and free text data elements within the medical record to warn of potential errors leading up to a planned surgical procedure. The second project addresses another global and local priority: prevention of healthcare-associated complications. We're using the power of precision medicine to evaluate the effectiveness of the VTE risk assessment that's performed upon every inpatient admission. The ability to synthesize information from the initial risk assessment and subsequent assessments through the prophylaxis and other care provided, and then follow that patient post-discharge into the ambulatory setting provides numerous opportunities to improve our ability to eliminate preventable complications. Our third current focus project involves machine-assisted abstraction of large volumes of clinical data. We submit data as a health system to 160 national clinical registries for quality benchmarking. An example is the National Cancer Database. This work currently is accomplished by a large workforce of experts across our system, and that workforce may be more efficiently deployed to other critical needs to assure mission success. So while we're working to our broader aims of a comprehensive risk system, we are moving forward with these three key projects. We're always open to potential collaborations, so please contact me if you would like to discuss. Thanks again.
Thank you. Up next is going to be Philip Rivera-Ortiz.
Hello. So the objective of this work is to develop a real-time trajectory optimization approach with finite time guarantees on safety. So the target applications are dynamic environments and multi-agent environments for which a priori information of the system trajectories are not known. So in this work, we developed a safe, finite horizon approach to nonlinear model predictive control through the use of control barrier functions. And specifically, the construction of control barrier functions through backup safety controllers is leveraged, which allows us to provide safety guarantees on nonlinear dynamics with finite actuation. The figure to the right summarizes our approach. First, the reachable set over the nonlinear MPC finite horizon is computed. Then the flow of the boundary of this reachable set is obtained for the different safety backup controllers. And the configurations that are close to safety violations are identified. And then these configurations are used to construct affine inequality constraints on the input only at the current time for the nonlinear MPC routine. We also developed a new approach to control barrier functions, which we call the leader-follower CBF, in which a selected leader is allowed to complete his task while the followers are ensuring that safety is preserved in multi-agent environments. If you click on the right arrow, a video, I think it's supposed to appear, Veronica? Or is I don't know if anyone is running the slides. If there are a couple of animations that appear if you click on the slides. Well,
Scott, can you give it a try?
Perfect. Can you click 2 more times? I think it'll make it easier. So the first video shows an application to the autonomous driving domain, where the leader is selected as a human driver, and effectively the follower, which is the autonomous agent, ensures safety. The middle video there is for a shared environment, which effectively shows that we're able to provide safe team-wide task completion guarantees in cooperative environments and also in adversarial environments. And along those lines, the final video on the bottom right shows a pursuit evasion game, which is an adversarial environment in which this approach allows us to balance task completion with safety. And the idea here is that the pursuers are actually trying to capture the evader, but at the same time, they need to preserve pursuer safety constraint. So if there are any questions or any ideas of collaborations, please feel free to reach out to me at philip.rivera@jhuapl.edu. Thank you.
Thank you. All right, up next, we're going to have Ryan Silva, Nick Safran, and Cam Hickert.
Thanks. Yep. Hi, my name is Nick, and today I will be presenting our work on autonomous cybersecurity orchestration, which was done in collaboration with Stanford's Intelligent Systems Lab. So kind of at the top here, you can see the general flow of data that goes through in the cybersecurity orchestration framework. And that is that the network generates data, which gets passed on to a SIEM, which is a security information and event management system. And then that system generates alerts, which get passed on to a SOAR, or a security orchestration, automation, and response system, which nowadays basically equates to an operator that has a set of playbooks. So the problem with this approach is it's quite limited in scope, and it's difficult to update because it relies pretty much entirely on expert knowledge. So it is basically a handcrafted set of rules applied by a person. And so what we'd like to do is shift the focus and perhaps more of the effort to a cognitive agent, which would hopefully free up the human to kind of address more complex tasks that perhaps the agent cannot do on its own, but automating most of that response. And so the way we've decided to approach that is to use reinforcement learning. And so here, our environment is a ship navigation systems network. Although that's really just kind of an example, and this really can be generalized to a variety of distributed control systems. So the agent's goal here is to prevent the attacker from gaining a foothold in the network by doing reconfigurations as necessary, while also trying to minimize its disruption to nominal operations. So this is basically a reward function based on the network's uptime, and it's weighted based on kind of some experimental data that gave us the importance of each node to the ultimate process, which is basically steering and controlling the ship. And so what you see on the right here is kind of some plots that show gauges for heading and speed, as well as the rudder's position and thrust, green being the desired position, and orange being the actual position. So what you can see at the top is an example of the system running without the defender in place. And there's quite significant deviation between the desired and actual position, which is kind of shaded in those strip charts underneath the gauges. And once we applied our defender, we see much greater correspondence between the desired and actual signals, which also correspond to the ship staying on trajectory. And this was even though the reinforcement learning's reward function is pretty much entirely in the network domain. If you'd like to follow up with us, please feel free to reach out to myself or any of the other folks listed on the slide. Thank you.
Thank you, Nick. Up next, we have Jeremy Brown. Jeremy, I believe you're going to be sharing your own slide for video. Oh, never mind. Our video looks like it's working anyways.
Oh, sorry, I was on mute. I just realized that. Let me just switch slides real quick. There we go. They're starting to play a little bit. I put too many videos in my presentation, apparently. But as I was saying, my name is Jeremy Brown, assistant professor in the Department of Mechanical Engineering at Hopkins. And I don't really have a project per se to talk about in the realm of assured autonomy, although in my lab, we do a lot of stuff related to human-robot interaction. This is more of a pitch to the IAA community I think a lot of times when we think about assured autonomy and autonomous systems, we're thinking about things that move around and navigate away from humans. But a lot of our systems are actually designed to interact physically with humans. And so I would say that we should be thinking about, as a community, interacting with interacting with humans in terms of assurance and autonomy, as much as we think about navigating with and collaborating with humans. And so in my lab, just kind of as a shameless plug, we work specifically in the area of telerobotic devices, upper limb prosthetic devices, in application domains of surgery and rehab. Our specific focus is in haptics and trying to understand how we perceive the physics of the world through our sense of touch and use that for humans in our dexterous control. And so when we think about building robotic systems that either extend our reach into environments that we physically cannot operate in, and we want to be able to establish that level of dexterous control and manipulation, or dexterous collaboration in the case of human-robot interaction, interaction, we need to think about these physical interactions and ensuring that our systems, as we make them more and more autonomous, which we are starting to do now, that they can safely, but also efficiently and kind of intuitively interact with their human partners and human collaborators. So that's it. If you want to learn more about what my lab is doing, talk about potential collaborative ideas, please feel free to reach out to me. My email, I think, just got put in the chat. You can find our website through the QR code listed there. Thank you.
Thank you. All right. Up next, we have Peiyao Zhang.
Hi, everyone. I'm Peiyao Zhang, a PhD student advised by Professor Marin Kobilaro from Mechanical Engineering. I'll talk about chance-constrained incorporated autonomous navigation in retina surgery. So retina surgery is one of the most challenging surgical procedures due to its high precision requirements, limited workspace, and dedicated tissues involved. A typical retina surgery requires the surgeon to insert a surgical tube and light source into the eye to operate on the retina tissue. In our previous work, we proposed a deep neural network to successfully predict the distance vector from current tool-tip position to the goal position based on the shadow of tool shaft. Then we can control the robot to navigate to the goal point autonomously. However, this method relies solely on the accuracy of network's prediction. What if the predicted goal is below the retina surface? So if we keep navigating the tool to this position, it will probably cause damage to the retina, which is what we want to avoid. So based on our previous work, we proposed a new method that combines real-time geometry estimation and chance-constrained optimal control to solve this problem. So the bottom left figure is our experimental setup. We use the steady hand-eye robot to control the navigation process. The measurement resolution of this robot can be as small as 1 micron along all 3 axes. So instead of predicting the goal point alone, we try to predict a lot of sample points around the goal point. Then we use these sample points to fit a small local area around the goal. Even though there may exist some outliers, as long as the most predicted sample points are accurate, we are confident about our geometry estimation. So we use optimal control method to generate a trajectory towards the goal point. The chance constraint is incorporated into the cost function to make sure that the probability of collision with retina surface is smaller than 1%. Our method requires transferring the chance constraint to deterministic constraint. The results show that even the predictable position, the green cross, is below the retina surface. The trajectory never collides with the retina. Okay, that's all I want to share with you. Thank you.
Thank you. All right, up next we have Aya Zurikli.
Hi. Veronica, I think this is not our slide.
Oh, let me try. Can we go to the next slide? Sorry, I may have put them out of
No
order.
problem.
Give me 1 second. I think I have it on my computer, worst case. Okay, I'll share my screen just to get it up.
Yeah, and if you want me to share my screen, I can do that too.
That's all right. All right. Here you go. Sorry about that.
No problem. I'm a research scientist working with Mark Dredzi, and we have been working on actually trying to build explainable models, like better explainable models that can be used in the mental health setting. So the main motivation behind our work, we use natural language processing, and these NLP models, they give us like kind of signals, they pick on language signals to tell us about the person, whether they suffer from certain mental health disorder. And the main goal is to actually help the clinicians in diagnosis and treatment. However, the issue with like the current machine learning model, especially the deep learning model, as everybody knows, that they really act like a black box, and we have a lot of issue with interpretability and explanations. And now, although a lot of work has been done in this area, we still are not really getting to a point that we actually have reliable explanations that we can provide the clinicians. So that kind of caused a delay in the clinical setting to incorporate such models. So our idea is actually to use one of the instruments that the clinicians use, which is in our case PHU-9, and it's a questionnaire that actually has 9 categories. For example, it has like sleep, self-harm, appetite, and the main idea is like actually if we build a model that use these auxiliary tasks, it can better predict whether the person has depression or not. And our initial model, it's a multitask learning model. It already does a better job at predicting whether the person is depressed or not, and also on the symptom level, as opposed to a single model that's only focused on predicting whether the person is depressed or not. But the second level that we do, that we are saying, okay, if we take if we build explanations on our model, as opposed to actually building explanations on the single model, these explanations that we build are more reliable and the clinicians can look at and make more sense of it. And our initial results actually support that claim. We didn't add them here just because like we need to do further review on the data to make sure everything is correct. We also added like one of our contribution is we actually build a gold data set of all the explanations so that like the community also later on can predict, like can better evaluate their explanations as opposed to a gold standard set. If you're more interested and you would like to collaborate or you have more questions, please feel free to reach out to me.
Thank you. All right. Up next, we have Carsten Box and James Spall.
Yep.
And I think you guys had, sorry, you had a video, so I just want to make sure it's working on here.
Yeah, I think it is. Can you see me?
I can see you.
Okay.
All right.
So does the video work on your thing? I saw it. I noticed that it was the first. It was you switched it, and I saw it working. Let's see. There we go. It's working beautifully. Beautifully. Okay. So so anyway, so I'm Karsten Botts. I'm a senior scientist at the Applied Physics Lab for Johns Hopkins University. And this is multidimensional swarming using cyclic stochastic optimization. And this is joint work with Jim Spall, who has a joint appointment between the Applied Physics Lab and the Applied Mathematics Statistics Department at Hopkins. So what we did is we considered a problem of multiple agents attempting to optimize some system-wide metric. And we did a case study for three-dimensional motion. So we assumed unmanned agents. They're going to cooperatively patrol a very large region to sense and detect and track and follow and survey targets. And we want to configure this fleet so that they can maintain what we call situational awareness of the region. These UAVs, they sense and they cooperate, and that implies that they share estimates of the targets and they share estimates of state information, and they efficiently allocate the workload, as you'll see in the videos that I'm about to present. The agents have limited ability to share information, so I assume if communication does happen, it does happen perfectly, but communication is not always guaranteed. And each agent, what they do is they select the motion to minimize a loss function, but this loss is imperfectly known. It's based on measurements, sensed measurements, and all sorts of guesses. So the loss that they're trying to minimize is stochastic, and it's also time varying. The time varying loss depends on the action of all agents. And we hope to make this method is flexible with potential to handle general multi-agent optimization in multiple uncertain environments. And so I've got these two videos for you, which Veronica was playing. And if you could play the first one. So in the first one, what we have two agents in blue tracking two targets in black. Okay, two agents in blue, boom, targeting two targets in black using the cyclic stochastic optimization. And you see that they stick with it pretty well. And this is what happens if, for three-dimensional motion, if you're looking straight down. If you're looking straight down, so the y-axis is north and the x-axis is east. And you see that the agents seem to divide the workload effectively, and they seem to stick with these things in perpetuity because those are the results, and it seems to work out pretty well. And that's looking straight down. And if you look east-west, you get the next slide. And if you just click the next arrow, Veronica, I think you see what happens. with in terms of vertical motion, not just horizontal motion. You see what also happens in vertical motion. So you see that applying the cyclic stochastic optimization algorithm, we get effective targeting, and we get effective tracking, I should say, and we also and we maintain situational awareness of where the targets are. We stick with them pretty well, and so that's my talk.
Thank you.
Yeah.
Up next, we have Nick Kantak and Nina Cohen.
Hi, I'm Nick Kantak. I'm a software developer at the Applied Physics Laboratory, and I'd like to present Instructive AI, which is an idea that emerged out of a challenge APL held earlier this year, in which staff were tasked with developing AI agents that would play with human teammates in the collaborative card game Hanabi. These APL agents had to compete with bots developed externally by DeepMind, Facebook, and academia. An APL bot won the challenge, and I'd like to describe how it was developed and the insights that followed. The bot was told initially what factors humans pay attention to and what value they profess to attribute to each of those factors. The bot then explored changes to those values that led to better performance. Something very interesting happened when we explored an alternative training approach. We initialized the bot in the same way, but instead of training to excel at Hanabi, we trained to predict the decision a human was going to make in the game. And in the end, we had an AI that highly accurately predicted the decision a human was going to make, but only by making significant changes to the values the humans said they used in the game. So essentially, the AI gained insight into a human's play that human didn't even have. More importantly, at the end of these two training processes, you have two agents, a superhuman agent and a human-like agent, but they only differ in the weights that they give to human factors. And this means that you can describe the difference between a human's decision-making and an ideal in terms of changes on the weights of human factors. An example of this is shown in the upper right. This is our superhuman Hanabi agent's appraisal of the strategic deficiency of my Hanabi decision-making. So you can see some things I do as often as I should, but other things like discarding, I do far too infrequently. And here I'm given explicit feedback on how my decision-making could be changed to better emulate an ideal. We are internally funded to explore this in FY22, both in the Hanabi case, but also in other AI assistance scenarios, such as medical diagnosis. If we have an AI that excels at some tasks, such as predicting melanoma from mole images, and if we are aware of the human factors that a doctor pays attention to in their diagnosis, it is possible to describe the AI's decision in the form of a variation on the doctor's decision-making. This can be useful if the AI is more effective, since the doctor is effectively trained on how to improve. But it is also useful in the case that the AI is less effective, since the AI can give an account for how its strategy falls short of the doctor's. If you are interested in learning more or have ideas to share with us, please feel free to reach out to me or Nina Cohen, the other PI. Thank you so much.
Thank you. Up next, we have Angie Liu.
Hi, everyone. This is Angie Liu. I'm a new assistant professor in the CS department of Johns Hopkins. I just joined last month, so it's great to have this opportunity to share my work with you. So I'm probably interested in trustworthy AI, machine learning method for trustworthy AI, and with a focus on how do we extrapolate safely from our training data, and also how do we get reliable and conservative uncertainties and confidence that will benefit downstream tasks. Can we have the next? Yeah, I want to use this Mars rover example to motivate our fundamental challenges in this area. For example, if you have a Mars rover that you want to put on Mars, next. You probably have seen some training data on Earth, but then when it's actually put on Mars, it needs to go beyond this training data. Next, it will need to explore unknown environment. And what makes things even harder is like there are unknown, like unsafe regions out there that the Mars rover needs to explore by itself. Next. Yeah, so if we do not deal with this distribution shift between this new domain and this training domain carefully, cannot really differentiate like this safe and unsafe regions. So how do we extrapolate from this finite training data, and how do we deal with distribution shift? Next. So we propose this idea to use a density ratio to quantify the distance between the source and target domain. Next. Yeah, this idea is like you use this density ratio to adjust your uncertainty estimates. And this density ratio needs to estimated from data, next, from the source entirety domain. So this idea is derived from a principal distributed robust learning framework. We use this to tackle many real-world tasks. Next. We apply this idea to safe landing tasks and achieve this 50% higher, faster landing while maintaining safety compared to the best performing baselines without human supervision. Next. We also apply this to safe planning problems in spacecraft. We generate this more informative trajectories in spacecraft simulation that achieve 30% higher success rate in satisfying the safety conditions. Next. And finally, we also apply this to this adaptive vision domain to achieve the state-of-the-art self-training domain adaptation with 60% improvement in the hard examples, which is when the example is very far away from your training set. So I'm very interested in generally in robustness and safety AI, and I'm looking forward to engaging more with the community here. If you're interested, I'm actively looking for collaborations and students. So if you're interested, feel free to contact me. Thanks.
Thank you. Up next, we have Phil Berlina.
Yeah, hi, thanks for having me again. Very quickly, we're working together with Professor Yingzi Chao at the Computer Science Department and Dr. John Hopkins at Johns Hopkins School of Medicine, and are envisaging a project, and this is more like a position, sort of like a proposal rather than something very specific at this point in time, that is surrounding the problem of pathophysiology behind the pathologic AI. And so what I mean by this is that if you look at trusted AI and all of the issues that are being considered, including security, privacy, safety, fairness, and etc., a lot of research work involves asking the question of if there is a problem, how do we measure it? For example, in case of fairness, we can say, how do we detect bias and how do we measure bias? Do we use, for example, accuracy gap? So the problem and the metrics is the if question, and the how is, what sort of intervention, what kind of changes can we make to the algorithm to make it more fair or to address issues of privacy or safety, etc. But there is relatively less work on the why, what, and where, which is, why is there a problem, and what and where is the root cause of the problem. And to us, leaving aside the question of why is a little bit akin to in medicine, being able to diagnose and treat the symptoms without knowing much about the pathophysiology of the disease, and it sort of misses out on other type of intervention that you could do, including having something that is more targeted or doing prevention. And so that's what we want to center our investigation on, and we want to bring together end user of healthcare AI, including Dr. John Hopkins, ethicists and algorithmic developers, to be able to propose different type of approaches. Some including automated diagnostic tools that will help us do some sort of forensic and ask the question as to why for this specific data and specific model, is there a problem in fairness? And it could be that, well, okay, there is a data imbalance or whatnot, or is there a problem in privacy? And it could be that, for example, there is overfitting of the model. And so from there, we'd like to also be able to propose targeted solution and intervention, as opposed to be able to do broad intervention that may have unintended consequences on the model itself. So we might be able to improve on privacy, for example, but then now we have something which is less fair or less robust in other ways. So this is the broad idea. If you're interested in this idea, please reach out to me and the other co-PIs. Thank you very much.
Thank you. Up next, we have Andrew Gwynn.
Hi, everyone. My name is Andrew Gwynn. My colleagues and I work at the Johns Hopkins Applied Physics Laboratory, and our focus is on building integrity for autonomous swarms, whether acting homogeneously or heterogeneously. The traditional approach to making sure that a swarm is doing what you expect it to do is to individually communicate with each member of the swarm, collect some sort of measurement, usually using some trusted hardware on the swarm platform in order to imbue trust into that measurement, collect the measurements back and appraise them to make sure certain attributes of the swarm, commonly what code is running, is correct. Of course, in the field, you want to avoid many aspects of overhead within this, such as the overhead of communication with each individual member of the swarm, the overhead of having a trusted module having to run on these swarm platforms and things like that. So the approach that we wanted to look towards was looking at observable characteristics and deriving measurements from those. We don't need to communicate with members of the swarm. We don't need to have special modules running on these systems. We are just able to observe them and derive measurements from that. Broadly, our approach is to capture measurements which look at sort of the behavior of these autonomous, or approximate the behavior of these autonomous systems over time, so that we're not merely looking at something like a geofence, which constrains where the drones can move, but looking at the types of behaviors that individual drones are engaging in and making sure that it generally fits how those autonomous systems should be behaving to pursue the mission. After all, since they are autonomous, they're making decisions of their own accord, and so you can't necessarily prescribe specific behaviors for them. And so the measurements that we focused on were entropy in their position and their direction. We calculated those over intervals of time and averaged them over a window, and we used this as input to clustering algorithms. We were able to look at this in several use cases. A couple are displayed here, and this was actually a poster that we used at a conference that we presented some of our work to. But we have scaled this work up to swarms of over 100 agents in simulation, engaging in a variety of missions, such as the search mission, where one agent was compromised and is trying to physically block off an area that the target of the search is trying to look for. We were able to detect that agent and pick it out of the rest of the swarm. But we have developed several other use cases. And in the future, we want to expand the reach of our use cases. And we also want to look at data sources which may not be able to allow us to attribute blame to any specific member of the swarm, such as radar traces and things like that. And thank you very much for giving me this platform.
Thank you. Up next, we have Yinzi Cao.
Hello, this is Yingzhi Cao. So this is a work that together with my colleague Fia Belina from APL. So the idea is try to access the threat to some complex AI systems. So beyond that image-based recognition, we try to analyze a real control system that can remotely control some self-driving cars. So the high-level idea is that the most previous work or concurrent work and most work on adversarial attacks that are vulnerable to perceptions or NLPs, but does not really look at the control system, because there are also more complex systems that in between the vision system and also other the LiDAR and radar systems that are equipped with self-driving cars. So the image we're showing here is that we played with a Baidu Apollo system, and together with the open pilot, and we showed that with a adversarial patch, we can mislead self-driving cars to, for example, turn left a little bit. And the final purpose that we have in mind is that if we have a truck that's driving in front of a self-driving car, and we dynamically change the patch that is on the back of a truck, and then we can use it to lead the car, so that when the truck turns left, and the car will also turn left, and the truck turn right, and the car will also turn right. So basically make the car is a follower of the truck. So our test bed is supposed to be the Baidu Apollo system that added with the open pilot, which has the a lane keeping functionality. We also have the Tesla autopilot that is provided by APL as well in order to perform the attack. So on the right side, we show some images about the lane being detected by the open pilot that has been incorporated with Baidu Apollo system. As you can see that we can indeed make the a different lanes that differ from the original lane that should be in the correct position. So thank you.
Thank you. Up next, we have our last speaker, Samik Chad.
Hi, Thank you all for coming to this talk. I am Samik Sadhu. I am a PhD student in the EC department. And my talk today is going to be on helping machines know when they do not know. So in today's world, AI-based decision-making processes are basically everywhere, and they are expected to replace human beings in a lot of key roles. But unlike machines, human beings have the ability to know when they do not know the answers to questions. Whereas machines do not have such built-in confidence measures, right? So for example, you can consider this neural network classifier here, which has been trained on some data. But during inference, this classifier can confidently predict the wrong answers, even if it's not sure about them. Or maybe even it has not seen such test data during training, and so it cannot really generalize well. So we propose to solve this problem by modeling the internal activations of this classifier on the training data itself. So now during inference, we would look at these activations and try to see how well this internal activations matches the model that was trained on the activations from the training data itself. So a few basic questions would arise from such a problem setup. So firstly, what sort of activations can we use? So we can look at the output of the classifier, we can look at the input, or we can even look at the layers between them. So the second major question is what sort of model can we use? So we can use some non-stochastic models, and the errors coming from that model can be used as a confidence measure, or we can look at stochastic models, which will basically model the distribution of the activations. And so the likelihood values coming from this distribution can be used as a confidence measure. And lastly, during inference, we need to know how much data is necessary before we can obtain a reasonable estimate of this confidence value. So these are the three main issues that we are trying to work on. With that, I would like to conclude my talk, and feel free to reach out to me if you have any questions. Thank you.
Thank you. And thank you to all of our lightning speakers today. All of your talks were wonderful. With that, we are going to move on to a final talk from David Silverberg for our flagship project.
Hi everyone, my name is David Silverberg, and I'll be describing the IAA Flagship Project activities. If you recall from Jim Bellingham's presentation, flagship projects are an essential part of the IAA strategy. It's where we take the results of our research, as well as other assured autonomy efforts across JHU, and apply them to real-world problems. We want to provide compelling demonstrations of how the methodologies and tools of assurance translate to real-world problems. The flagship projects are really the next phase of the research and development agenda. The flagship projects are mechanisms for demonstrating quantitatively the extent to which technologies and policies improve assurance of autonomous systems for the benefit of society. These technologies and policies may have been developed by IA-related seedling projects or by other JHU projects. At the core of flagship projects are applications that have a baseline component that operates as expected under normal conditions, but is subject to not operating as expected under stress or adversarial conditions. The intent is to demonstrate and assess the increased level of assurance of applications after they are augmented with technology and/or policy enhancements. The IAA research portfolio consists of the 10 research projects that you heard about earlier. They address some of the hardest problems in assured autonomy. They were selected because they cover a broad and important swatch of assured autonomy issues. They can be categorized as safe and reliable, secure and resilient, seamless integration, and beneficial and ethical assured autonomy. These categories, however, are from the perspective of the common assurance challenges across many autonomous systems. The IAA has also defined important domains to which these challenges apply. They are autonomous vehicles, smart and connected communities, and healthcare. These domains were selected because of the formidable capabilities that JHU has in these areas. The list of domains is by no means exhaustive, but these are the initial domains that the IAA has chosen to focus upon. IAA's initial foray into flagship projects will be in the area of assuring autonomous systems that will improve healthcare and patient outcomes. We chose assuring autonomous medical systems because of the strength of the Johns Hopkins Medical Institute, the strength of the medical robotics capabilities of the Whiting School of Engineering, and the strength of APL's ties to military medicine. We released a call for information to the general JHU community in May of 2021. We received 14 responses that roughly fell into 4 categories, which are hospital care, emergency response, home care, and infrastructure. These are listed on this slide. If you notice under hospital care, we have topics like mechanical ventilation, infusion pumps, patient monitoring, communications, cleaning, and restocking. Under mass casualty and emergency response, we have both military and civilian health and emergency response, trauma diagnosis and care. From the home care perspective, we have home care robots, wearables, shipboard surface Navy healthcare, and autonomous medicine for spaceflight. Under infrastructure, we have medical infrastructure and interoperability for medical autonomous devices. There's fairness and privacy, and cybersecurity for wearables. The first category of healthcare flagship projects under consideration focuses on hospital care. The Whiting School of Engineering has a strong relationship with the medical school with respect to medical robotics. This effort would combine different capabilities in a holistic sense and demonstrate how we address the assurance issues listed on this slide. So again, the topics are mechanical ventilation, infusion pumps, patient monitoring, cleaning and restocking, calls, communications, and the assurance issues that we would be addressing are reliability, regression testing, safety boundaries, trust monitoring, ethics, privacy and fairness, reliable and interactive communications, and teaming. The second category of healthcare flagship projects under consideration focuses on mass casualty and emergency response. We are considering both military and civilian applications. APL has programs in both domains, and both domains are similar. From a military health perspective, it is anticipated that autonomous technologies will help save the lives of warfighters in the critical time between injury and medical personnel arriving. Similarly, autonomous healthcare technology will help save the lives of civilians in the critical time between injury and medical rescue arriving. This effort would address capabilities in a holistic sense and demonstrate how we address the assurance issues listed on the slide. For example, issues like explainability, predictability, performance monitoring, accountability, diagnosis, safety boundaries, trust monitoring, and data integrity, privacy, and security are all some of the major challenges of autonomous mass casualty response. The third category of healthcare flagship projects under consideration focuses on home care, perhaps even as an extension of the hospital itself. Generally, patients are discharged from the hospital because they are no longer sick enough to remain at the hospital. However, their prognoses for recovery depend heavily on how well they perform their exercises and therapies during follow-up appointments or at home. Unfortunately, not all patients keep up with their regimens. They have difficult times coming to the hospital or other facilities for their therapies and exercises. The more that autonomous systems can help patients at home, the better their prognoses. In addition, long-term health care can be significantly improved through autonomous systems technologies. The home care flagship effort would address capabilities in a holistic sense and demonstrate how we address the assurance issues listed on this slide. An important aspect of all healthcare flagship projects is the infrastructure used to support distributed systems and people. We expect infrastructure to play a significant role in the flagship project we ultimately select. Now, I will describe the second domain of interest for flagship projects. The IAA shuttle is coming to APL. Well, almost. We're awaiting final approval. This will be the platform through which we explore autonomous mobility. This slide lists a number of the research topics that span technology, ecosystem, and policy and governance. Ultimately, we are looking to increase trust in autonomous vehicles. Some of the potential demonstrations are technical, some are human-machine oriented, and others are policy-based. There are aspects of OLLI that will tie into other efforts at JHU, including unmanned teaming, smart campus, and modeling and simulation, just to name a few. If you have an idea for assured transportation, please contact Ed Pavelka at the address shown on this slide. Finally, I will describe the third domain that we are exploring for flagship projects, which is smart and connected communities. IAA has been working with several cities to develop concepts for smart and connected communities. We are early in the process, but this looks to be a place where JHU can demonstrate real innovation. Finding the right level of contribution is challenging. It is easy to identify the next delta in smart city capabilities, or to identify very futuristic concepts that may become obsolete. We are currently seeking challenges that are roughly in the 3 to 5 year time horizon. We are regularly meeting with representatives of multiple cities across the country that are actively pursuing smart city efforts. As I said before, we are in the early stages, but this looks like it will be an exciting and fruitful venture. If you have ideas for flagship projects that demonstrate assurance of autonomous systems within smart and connected communities, please contact me. We are looking to team with people across the JHU enterprise. We are also looking to team with external organizations to jointly fund and develop the flagship projects. If you want to get involved or have ideas, please reach out to me. I look forward to collaborating with you. The next part of the agenda are breakout sessions to discuss flagship projects. If you have any ideas or at all curious about some of the flagship activities, please join us in the breakout sessions. It was a pleasure speaking to you, and I look forward to hearing from you in the future. Thank you. Actually, this is David. So the breakout sessions will occur very soon, around approximately 2 o'clock, but there's a wrap up given by Carol Lapointe and Tony DeBora.
Kara, you're on mute.
Oh, can you guys hear me now?
Yep. Yes.
Perfect. Well, we just wanted to say thank you to everybody for coming. Hopefully, if this is your first time interacting with IAA, you've learned a lot more about it and you're excited about collaborating. A lot of exciting ideas in the Lightning projects. It's great to hear an update on all of our seed project work and our policy and governance work. So we hope that you will join us in the breakout rooms. It's just a time that we have for some informal conversation that you can talk to Jim. You can talk more about flagship projects, about some of our ethics and governance work, about smart cities, or anything else you want to talk about. So thank you so much. We really appreciate your time. And with that, I think, Veronica, can you post the breakout rooms?
I have a few words.
Oh, hey, there's Tony, sorry.
Yeah, could I share my screen, please, Veronica? I have one slide to show.
Sure. You should be able to override.
Okay, let me just get the right slide. Okay. And it's, here we go. Okay, so I wanted to wrap up this portion of the meeting, first of all, with a thank you for hanging in there and listening to all of the information about all of the work, the great work that's been done across Johns Hopkins. But I wanted to kind of stress and almost literally drive home the point about how these technologies are really coming to fruition. This is one example that probably will impact many of us as we drive around in the state of Maryland. And you may not be aware that as of a couple of weeks ago, there's been a process in place for the Maryland Department of Transportation to authorize truck platooning on highways in Maryland. And it's very interesting. This is constrained, a maximum of 2 trucks, and each truck will have a driver for now. And what's really telling is that according to the website, and Karen and I are involved in the working group that is responsible for overseeing this kind of technology in Maryland, but it's basically a self-certification process by companies that want to have a license to platoon in the state of Maryland. And so there's self-certification followed by a review by a number of agencies, but it's a paper review, checking off boxes and so forth. And so, and basically it certifies that the platoon operator has implemented all of the processes to ensure the safety of the platooning. So this is, one could view it as perhaps an evolutionary step. Maybe it's no more than maybe you could view it as aggressive, stay in lane or adaptive cruise control, I guess. But all of the topics that we talked about today, literally all of them come to play at some point in this type of system, from unexpected combinations of inputs to adversarial attacks, to ethical questions, to even liability legal issues. So I think the point here is that these technologies are rushing to market. And so these technologies impact every aspect of our lives. And so hopefully this is kind of a call to action and inspiration that what we're doing here is important, really matters, and will have a lot of impact. Thank you.
Thanks, Tony. So with that, we invite you to go over to the breakout sessions.
Do we have the URL posted for that?
I've put it in the chat and it's on the screen now. I'll send it in the chat once more just so you all have it.
Great, thank you.
And just so you guys are aware, that bit.ly URL that you see on the screen is just a shortcut to take you over to the Zoom in case you have to manually type it in.